Okay. Let's try this out. There are no there are no reasons that this should not be a great class. Okay, no reasons. Hopefully you already found yourself in the right class, or else there is a reason this would not be a great class because you're in the wrong one. But this is a course called Violent Earth. Violent Earth. Now, first, before we dissect that little term violent and what that has to do with the perspective of the Earth, the intro slide right here is of our beautiful blue marble. This is a picture taken from the Apollo astronauts, Apollo 17. This was one of the Apollo missions that the astronauts were able to look back and see a fully illuminated Earth. Previous missions to this, the Earth was in such a way that it was not illuminated fully by the sun. So in this case, the astronauts were must have been moving towards the direction of the sun, so the sun was behind them to then fully illuminate the Earth. Now, besides those fine points, when this picture was transmitted back to Earth, this picture is responsible, maybe not solely, but at its time and in its place for the environmental movement. Now, there's a lot of other background to all of this, but fundamentally what moved people to come on board to maybe an environmental movement and to look at the Earth as an environmental entity, as in an environment that we all share together, each human, each tree, each different species. What gave us that ability is this picture, to see the whole Earth on one image. You can't undo this. You have to see that it is all connected, right? That the clouds and the water of the oceans and the land masses and the ice caps all connected, one system. Okay? I love this picture. I love this picture of the blue marble. It is very enigmatic. So let's talk a little bit about Violent Earth then. This is kind of what our roadmap of today looks like, very first class. Hopefully I'm not laying too much on you already. But our roadmap today, we're going to talk a little bit about what natural violence is. We're going to take a long detour into kind of that idea of the whole system, the Earth system sciences and other classes that are taught relating to those Earth system sciences. And then we'll translate that into a discussion on deep time. So what's shown here is first maybe a discussion about scale. We're going to talk about all of the systems, all of the pieces intertwined. And then it's really important that we don't just talk about how that is now, but also how that was in the past or how that may be in the future. Okay, the future thing I'm not going to touch with a 10-foot pole. Right? I'm not in the business of predicting the future. However, I am in the business of looking at rocks. And rocks tell us, amazingly, a whole lot about the Earth's past. In fact, the rocks are the only record of Earth's past. There was nobody writing this stuff down 1,000,000 years ago, no person with a written language. It's all written in the rocks. So if we want to understand anything about Earth's past, whether that's a millennia ago or 500 million millennia ago, we need to look at the rocks. So that is the science that I've taken to my heart. I'm a geological scientist by training, and I'll certainly try during this course to take some of that exposure that I've had in the past about this good Earth, about its history, the past, about its fundamental materials, and translate that at least in an ounce to you in a nice solid 10-week course. Okay, so here's our roadmap, but let's come back to violence. Okay, here's just a nice little, what would you say, like Google Dictionary or something, right? All I did was just Google violent. And here's what comes up on Google, violent. Now you can Google that for yourself and look at the definition there. but I pulled out one piece of that definition that's very specific to this course. Okay, and that's what's highlighted here, a destructive natural force, very strong or powerful. That's what we're going to be talking about in this course. So that's what I'm going to focus on here, are very destructive natural forces that are very strong and very powerful. So that also makes them quite rare. Most of the things that we're going to address in this course don't happen all that often. In fact, many of them have only happened once in the entire 4.5 billion year history of the Earth. Okay? These are rare events. These are big events. These are powerful events. And many of these events are incredibly important leading up to your and I's lives here on Earth. Okay? That fundamentally, some of these events shaped not only the Earth, but shaped how life on Earth got a foothold, evolved, and has taken root on this planet, and in fact affects this planet in some very, very deep ways. Again, major events we're going to discuss in this course. So when we're talking about violence here, we're not talking about the violence that you might hear about going on out on the streets or something, right? We're not going to talk about gun violence. We're not here to talk about human-on-human violence in any way, right? That I really don't care about that. Find that in a sociology class somewhere else. Well, actually, I am a human, and I do care about that very, very deeply. But that's not the scope of this course at all. In this course, we're going to sort of peel away from the sociologic implications of the human world. We're going to come back to the natural world and focus on the natural history of this planet that we stand on. And through that lens, peculiarly, we're going to focus on just the big, bad things that have happened in Earth's past. The biggest and the baddest. So really, this is a survey class of all of Earth's worst moments, right? You could kind of make a nice 4-minute top 10 video of Earth's worst moments and post it on YouTube. And that's basically what this course is in a long 10-week format. So if you could do it in 4 minutes on a YouTube video, then why am I going to talk at you for 10 weeks about this stuff? Because it's in the details, right? Anybody can put something up on YouTube, or, write some blog of material about these events. But really, it's the details that I'm here for. As a trained scientist, as a geologist, as somebody who's read this material, the raw material from the scientists that produced this data or collected the data and then analyzed this data to reach some probable conclusions based on those data. That's what I want to lead you through. I want to lead you through some of these supporting details so these things don't just seem like wild claims that came out of nowhere that somebody is spewing, like they're myths, like they're the mythology of the Greeks or something. No, this isn't mythology. This is real world stuff. This is the planet that we live with, and it has been extremely violent in its past. Okay? We'll come back to the format and the structure of this class in a little bit, and I'll say more about that. But this is the kind of violence I'm talking about, right? Is volcanism. This is a pretty good example of something that if you live down here in this town, you might consider this a violent event in your backyard, right? Maybe you're displaced from your home, there was an evacuation warning, maybe there's ash that's raining down on your home, or maybe like the fairly recent events on the big island of Hawaii, maybe there's lava that's flowing down the street that you normally drive on to go check your mail. That's kind of a violent event from this perspective, okay? Now, this is an average volcanic event. This is the Mount Pinatubo eruption in 1991, 1992. And this was a really big event, okay? Not taking anything away from that. From the human eye, this was extremely impactful. Now, still, on the scope of this course, this is small. Okay, we're not going to talk about average volcanism in this class. We're not here to talk about Mount St. Helens, average volcanism, or Mount Pinatubo, or any Mount Fuji eruptions, or Krakatoa eruptions, Tambora, any of these volcanic events that you've heard of in the past. We're really going to talk about things like super volcanoes. Those types of volcanoes that when they erupt are incredibly devastating, not just to the local population of Earth's creatures, but to the region, right? Maybe the continent and maybe the globe, actually all of the above. When supervolcanoes erupt, they are incredibly disrupting. We will focus a little bit on supervolcanoes, and those are just one of the large, violent, destructive events that we're going to focus on in this course. Okay, but I think this paints a picture, hopefully to you, of the aspect of violence that we're going to talk about in this course, right? I imagine when you signed up for this course and you were telling your buddy about it, or maybe you're telling your mom, she goes, "What are you taking a class about violent Earth? Don't you hear enough violence in the media?" Right? Aren't there enough media outlets talking about mass shootings and wars and things like this? Absolutely, right? But that's not what we're talking about here, right? This violence, you can go home and tell your mom, is the raw violence of planet Earth. The raw violence that every single creature that has ever lived on this planet has dealt with since day one, because this planet is a violent planet. And just because we live in a time of relative quiescence in our short human history that we've been able to record this stuff, doesn't mean that it's not a violent planet. Okay, so we're going to take a look at events quite larger than average volcanism. Okay, so I wanted to also stick in a little, you can kind of look at this as an advertisement, right? Here are all the other classes that you can take. But really, this does have a place besides convincing you that you need to take more physical science classes. But also, not just taking my classes or wherever you transfer to or other classes to take these physical science classes. This is also meant to set the background of what we refer to as the Earth systems sciences. The Earth system sciences. So all of these independent classes that are shown over here, that are shown as like 110, 109, so on and so forth, these are individual classes that all weave together. They all weave together in this larger umbrella science called the Earth systems sciences. You have to understand the components before you can understand the system. You have to understand this component before you can understand how it interacts with this component. Okay, so a portion of this class is going to be dedicated to the interaction of all of these systems. Because you're not in Geology 106, General Geology with a lab, where I'm going to be showing you rocks or showing you, tectonic processes and the nuts and bolts of that science. Instead, this is a much zoomed out view of the planet, where we're looking through its entire history, the last 4.5 billion years, and we're talking about these really large, big events that have impacts on the geosphere, the biosphere, the atmosphere, all together. So I am going to pump a little bit of this Earth system sciences perspective, and that starts here with explaining a little bit about these classes. So what can be found here, the Geology 201, or the 200 level sequence, we have a little bit about Earth's interior, Earth's exterior, and then generally what's called Geology 203 is historical geology, which is really looking at these two earlier perspectives, the surface, the Earth's dynamic surface, rivers and streams, and the Earth's interior, and looking at both of those things through time, through the evolution of Earth itself. General Geology 106 here at this institution is really a survey class of all of those processes, a little smidget of history, a whole lot of Earth's materials, rocks and minerals, and a little bit about, the morphology of rivers and streams and why that mountain is there and why that valley is there type of stuff. So if you're into survey classes where you just want a broad understanding of that science, then General Geology 106 is a good course. In General Science 107, I like to call this space-time stuff. Then we also have Oceanography, which is General Science 108. We have Meteorology, General Science 109. And one of my favorite classes, General Science 110. It's called Energy. That's just it. No ology to it. It's just energy. Okay, we'll go back through that in just a second. Now, slow down a second. I want to point out in Geology 201, what are some of the specific things we're talking about here? What are some of the specific concepts? We have plate tectonics and the formation and the breakup of supercontinents. It takes up a large portion of this course. Yeah, you need to know Earth's raw materials, rocks and minerals, structure of the Earth, deformation of Earth's crust, how the Earth's crust rifts apart to form oceanic crust, and how it collides together to form mountainous boundaries. Also, how the process of subduction, where an oceanic plate subducts beneath a continental plate or another oceanic plate, leads to volcanism. Okay, arc volcanism, we call that. And then, of course, before talking about any of that stuff, before getting to know how the world functions, you have to know the world's materials, right? I like to say that the Earth, or some of these classes, like General Science 106 or Geology 201, is reformulating your relationship with Earth as a friend. The Earth is my friend. That's really how I see the Earth. It's a peculiar relationship. It's a peculiar friend that could clearly devastate me in any volcanic eruption, right? That friend's got the upper hand. But what I really mean here is just like any new friend that you try to make, that you're going to make. Some of the first things that you do when you meet a new friend are, you exchange names. Hello, my name is Sammy. Yes, right? You get to know each other by naming some things, right? Sort of an understood portion of that friendship, because this is one human walking up to another human, is the understood between them is that they're both humans, right? I know that I'm a human and I'm made of flesh and bones, and you're also a human from my observation, and you are probably also made of flesh and bones. But the Earth is sort of a different style of friend. It's not made of flesh and bones, and that confuses us sometimes. So we really have to ask the first question of this friend, which is, what are you made of, right? Earth answers, I'm made of rocks and minerals, right? So there we go. That's a half of the first geology course, is getting to know what the Earth is made of. That would be Earth's materials, rocks and minerals. And then the second question that you might ask a friend or somebody you're getting to know is, what do you do every day, right? How do you function? Where do you work? Where did you just come from? What kind of car do you drive? What kind of bike do you pedal? There are these fundamental questions about what do you do? Do we have anything in common? Is usually what you're trying to get at there is the result of this question. But we need to ask that same thing of Earth, and that's all of this other half of, say, Geology 201 is not only what are you made of, but how do you function? What is your daily process? Or in the Earth's case, what is your millions years long processes that you undergo? Again, these things are relatively foreign to most people. So this does seem sort of weird to us, right? To get to know the Earth in this sort of way. And that's why I frame it this way. Frame it as the Earth is your friend, and you want to get to know this entity as a friend, and you start to ask different questions. If you treat this as a subject rather than an inanimate object. I'm not saying that the Earth is animate, but I'm saying that by treating the Earth or Earth's processes or Earth's materials as an animate subject, then you inherently start to ask different questions and you seek different things relating to its function. Then the last portion of many of these classes, almost all of these general science, physical science classes, is a component of what is our relationship, right? Okay, so you got to know the Earth's materials and how it functions. Next step with your new friend is, how do we relate to one another? What is our relationship, right? Are we good basketball buds? Did we just meet at the carnival? Or is this like a thing, right? Are we going somewhere romantically with this? Those are all relationships that you kind of want to know as it's developing, right? You have your idea, that person has their idea, and then your further interactions tend to pursue one or both of those people's ideas. And similarly with the Earth, we have an inherent relationship with the Earth. And sometimes it seems like a one-way relationship because I'm always up here in my brain, right? I'm me, I'm human. I don't think about me from the Earth's perspective very often, right? But that's what I would ask you to do. It's what, in fact, I am asking you to do in some cases in this course, is to think about the Earth's relationship with you, right? How do you guys give each other feedback? What goes back and forth? Really, this can all be boiled down into resources. I mean, not solely, right? There are many other maybe poetic things that you might say about your relationship with Earth, but fundamentally, you and I are Earth resource harvesting machines. That's pretty much what the biosphere does, is we take the resources of the Earth that are imbued with energy. Mostly that energy comes in from the sun, but that energy can also be trapped in the form of minerals. Maybe some of those minerals have radioactive energy, or this could be the raw energy, the primordial heat of accretion that's emanating out of the Earth, like say at mid-ocean ridges, at black smokers, where you have communities of organisms that are living off of the heat and the chemistry of those areas. Point here, that last point, is the relationship, okay? And while in this course, we're not going to dwell on those three series of questions, what are you made of, what is your function, and what is our relationship, the relationship is ultimately where we're going in this course, okay? We'll look at the syllabus in a minute, and we'll see the narrative of all of the events that we're going to focus on. But ultimately, I want to know about me, right? I'm human, I'm selfish, me. So we're going to talk about that, right? We're going to focus on you, and how this course brings meaning to your life as a business person or a lawyer or a sports medicine therapist or wherever you're going in your collegiate career. You happen to stumble into my class, this Earth Science class, maybe intentionally, maybe not, but hopefully what you leave with is a fundamental understanding of the Earth as a friend, or just a person, you don't have to call it a friend, how it functions, and what your relationship is with it. Okay? Now in Geology 202, we do very similar things, right? 201 kind of lays that foundation, but 202 is all about the superficial processes. This is a little bit less abstract than talking about rocks and minerals and looking at these things and plate tectonics and all of this stuff. Most of that stuff we can't see, right? Yeah, you can see a rock, but half of the rocks that I bring you in the lab are not rocks you're ever going to see again, right? They've been accumulated together to bring in a little box to show you here's what Earth is made of, okay? Now, your experience with Earth since day one has been the observable stuff that you see on the surface, right? You don't see the core, ever, right? You don't see the Earth's mantle, you don't see subduction, you probably won't see volcanism, maybe on some cool YouTube videos from the Kilauea eruption. But my point here is that the superficial processes, the surface processes of Earth are what are most accessible to your eye. So one of the concepts we would talk about is mass wasting. A mass, like, a mass of something, that wastes away. It's being wasted away. So there's this element of movement of material. A mass wasting event is like a landslide, a rock fall, an earth creep, These are all different types of mass movements or ways that the Earth, via gravity, right? The Earth is massive, and everything on Earth is held in by that mass, the relationship of mass and the proximity to it, and that's known as gravity. Well, gravity always acts towards the center of the Earth. If you have very big, steep, unstable slopes, then eventually those slopes, because of gravity, fail and over time become flattened or become, over weathering and erosion become flattened. And that's really this course in a nutshell, is we're looking at how Earth's processes allow gravity to make Earth flat. But of course, Earth will never be flat because it is, as you learned in Geology 201, it's dynamic, it's ever-changing, it's tectonic, it's volcanic. So there are always mountains and tectonics. So in 202, we do look at mass wasting to even out the surface. We look at surface water movement, rivers, lakes, streams, glaciers, groundwater, which is extremely important to your livelihood and is probably not something you think about very often. Most municipalities, and if you live out in the country, you probably live off of a well, right? Just like here in Ontario, Oregon, the municipal water is derived from a couple of wells that's then treated and disseminated to all of you good folks, or you can go over and use the water fountain in the hall. But that water comes from the ground. That's why we call it groundwater. And that's a type of water that we don't often think of. And I like to draw attention to that in this course. And then coastal erosion, deserts, these are all concepts that we focus on in Geology 202, Earth's processes. Now, as I said probably 10 minutes ago by now, Geology 203 is a combination of all of these things. Not in the sense of trying to do it all at once, but in the sense of taking those fundamental processes that we learned about, whether they're tectonics and interior dynamics, or surface processes, river movement of sediment, and looking at that through time, with a time component. So this is adding that other crucial dimension here. So what we end up talking about in Geology 203 in historical geology, or Earth through time, is we end up talking about ancient volcanic eruptions and how we can see evidence for those. So how do we actually read the record, the rock record, to tell us about these things? We also talk about larger tectonic reference frames. So though it may be addressed in Geology 201, what's known as the Wilson cycle or the supercontinent cycle, where continents collide together to form large land masses. You may be most familiar with Pangaea, really the youngest of the supercontinents. And when Pangaea broke up, it opened, zipped apart from the Atlantic Ocean, and that left behind Africa and South America that have that peculiar fitting shape to them, right? I'm sure you've all noticed this before. Maybe, when you were in 5th grade earth science, your teacher conveniently showed you this, that you could rip a piece of construction paper apart and fit them back together. It's all perfect, right? That's Pangaea, and that's only the most recent of the supercontinents, right? So they collide together and they break apart, and then eventually they collide together. It may not be on the other side of the globe, but processes, internal processes like subduction, volcanism, allow them to form supercontinents again. So we take quite a bit of time to look at the different supercontinents that have formed. And then a large component of historical geology is fossils, right? Looking at Earth's ancient creatures. So today, if you're looking at a shrew from South America, or if you're looking at an orangutan from Indonesia, you are looking at biology. You're looking at living creatures that we can name a genus and a species today. We can classify that taxonomically today. Now, those species exist, right? They're not extinct. How about the animals that we dig up that no longer exist, right? Like Velociraptor, Titanotheres, or trilobites. These are fossil creatures, and this is not the discipline of biology then, right? This is the discipline of paleontology. Paleo, ancient, looking at ancient creatures. And in historical geology, we spend quite a bit of time looking at these ancient creatures and looking at how people have reconstructed their environments and their ecologies. But also, these creatures serve, well, they have a great service to us as geologists. These creatures, the fossils, not the actual creatures themselves, but they're leftover remains that have been fossilized in rocks. This is one of the greatest markers of time. This is one of the things that helps us to understand what layers of rock are older and what layers of rock are younger. Now, there's a principle in geology, the principle of superposition, that suggests oldest rocks are on the bottom and youngest rocks are on the top. Okay? Makes sense. But what happens when tectonics gets involved, right? And these things get faulted and flipped around up this way. Well, guess what? Then the rocks are not the oldest on the bottom and the youngest on the top. So we have to rely on other skills, other cross-cutting relationships to look at these features and to tell what is older and what is younger, right? This is what's called relative age dating. Now, alone, that can get us pretty far if we add in processes as well. But fossils and fossil assemblages, an assemblage is kind of like an ecology. It's not exactly an ecology, but an assemblage would be the common fossils that are found in that rock, right? In that strata over there that has 5 or 6 different species of shelly creatures that are within that. That would be a fossil assemblage. And if we can use fossil assemblages to compare one rock unit that was, say, in northern France to another rock unit on the British Isles, then we can make a correlative relationship between them, that the same organisms were living at the same time, and they weren't in the rocks below, they hadn't evolved yet, and they aren't in the rocks above because they suffered extinctions. Okay, that's what happens to animals. 2 out of every 5 species that evolve every million years goes extinct. So fossil assemblages and looking at these fossils help us to organize all of these rocks into some way that it makes sense to us. And if it were not for people looking at fossils for the last, well, let's just narrow it to the last 300 years. I'm sure people have looked at fossils for a lot longer than that. But as far as a scientific reference frame, the last 300 years or so, looking at fossils has really helped us to decipher Earth's history. It's the details, again, that are really important here. Okay, then in Geology 106, as I mentioned, this is a survey or a mix of all those geoscience topics. Now, let's step out of the geology world for just a minute, and let's look at some of these other physical sciences or the other Earth systems that are working together here on Earth. General Science 107, as you can see here, we have the planet Venus, and then a galaxy. This is the Andromeda Galaxy, some meteors, and then what's meant to be shown here are the 3 stars of Orion's belt, and the rest of the outlying stars. General Science 107 is astronomy. Astronomy is the study of the night sky. Astronomy differs quite a bit from maybe other types of physics, like astronomical physics that are looking in cosmology that are looking a lot more deeply at space, or say like at time, like black holes and the theory of general relativity and this kind of stuff. That's not what we address in General Science 107. Instead, in General Science 107, we kind of keep it local. Right? We talked quite a bit about, the physics of light. We need light, or we use the physics of light to detect the stars and to detect our local area, the planets, the other wanderers that are out there like us, that are wandering around in this orbital elliptical pattern around our central star, the sun. And General Science 107 is really a focus on all of those topics. Again, we're going to keep it local. What I mean by keeping it local is we're looking at the solar system primarily. We also look maybe towards the end of the course just a tiny bit on the origins of stars, birth of stars. We really don't focus a whole lot on cosmology and Big Bang. Of course, it's addressed, but this isn't a deep level course on answering the questions of the universe. Instead, I decide to focus my time in General Science 107 astronomy on something that's really meaningful to you. Yeah, the origins of the universe and black holes might be really meaningful to you in some academic sense, but the night sky is something that you see every day, right? Stars up in the night sky are something that you probably see every day. The phases of the moon, you see, a couple times a month when it's full or when it's about full or when it's, waning away. My point here is that I find it very valuable in astronomy class to focus on stargazing, right? Naked eye stargazing, binoculars, a little bit of telescopes. I like to dig in and to look at the map of the heavens, talk a little bit about the ancient mythology from all of the amazing cultures and in the last thousands of years that have looked at the night sky and have woven stories about those. I think that's fun to talk about. And those stories help us to remember the constellations. They help us to look up at the night sky and go, yes, over there in the east, in this case, so this classroom is arranged in this way where you are to the north of me, and this is to the east where the sun will rise tomorrow morning. But guess what? What's rising right now is the constellation Orion. It's basically up here. He's mostly risen up in the sky, and then the star Sirius, the dog star down here at his lower right, will rise momentarily. Right? My point here, I guess, is that stargazing is a lost art. Stargazing, looking up at the night sky and identifying constellations, is not something the average Joe knows. And it's not because we don't want to know. It's because we don't often find ourselves in that capacity to do it. So in General Science 107, I take a large portion of the course to not just focus on planets and their makeup, their atmospheric compositions, and some sort of this space travel type of stuff, right? But instead to empower you to look up at the night sky and to see the constellations, to see the stars, to look around at that roadmap. And that's something that connects you to all of our ancestors in the past. Because up until, 80 years ago, maybe, the sky was our television, right? The sky was the place that we made drama. The sky was the place that we looked to for stories. Okay, yeah, there was radio, and yeah, there was books and this kind of stuff. But the further you go back, the more important that the night sky was to your ancestors for the stories that we wove together, the dramas that you might see on a Hollywood movie screen today are derived from stories that were told orally by the movement of the stars and the heavenly bodies around you. Okay, this is one of my favorite courses for that aspect. And where this fits into the Earth system sciences perspective is knowledge of the solar system. The sun is our primary energy producer, right? It's the big boss of the solar system. It's in the middle, and it's what produces all those photons that fly across the 150 million kilometers of space to interact with the Earth. So in the Earth system sciences, the heliosphere, the sun, the fire, is the production of energy, and that's where we start in the Earth system sciences, is energy. Okay? So here's kind of how we look at this course through a caveman perspective and a starship perspective. Okay, General Science 108, this is a course called Oceanography. This is also a very very fun course. Oceanography is not the study of exclusively ocean creatures, right? That would be marine biology, right? Where their marine biologists would be focusing on all the microorganisms, the trophic, the food chains, all the way up to your gray whales and your sharks, and how that material gets onto land and the ocean as the base of the food chain. Okay, that's the realm of marine biology, and in oceanography we certainly discuss that, right? That is within the realm of oceanography, but really oceanography has a focus on processes, right? Processes like coastal processes, erosion processes, wave processes. So what is the origin of waves, right? Why, when you go to the coast, say of the ocean or of a lake, do the waves just keep lapping on forever and ever and ever and ever and ever? And that's not the tide. The tide is fundamentally different. The tide is the slow raising and lowering through time because of the moon cycle. When the moon is on one side of the earth, it adds enough gravitational force, enough mass to pull on that liquid sphere of the earth, and that pull creates a bulge on this side, which ends up creating a bulge on the other side, and then two thinner areas. So you have two high tides and two low tides. Okay, so it's the processes in oceanography that we're really getting to. That is the main focus of the class. Currents and circulation, the interaction of the ocean with the atmosphere to form what we typically call weather, or if we look at that through time, how the oceans impact climate. And then we get to marine biology, ocean biology, right? I mean, that's the fun stuff, I mean, everybody likes critters. Well, I'm no biologist, so I'm not really that fond of critters unless they're dead and fossilized. But, everybody likes critters. I certainly love to go to the Oregon coast and go to the tide pools and look at the multiple species of anemones and the multiple species of starfish that are there. There is something really fun about that type of identification too. Yeah, even for a rock nerd, right? So in this course, there's often a trip to the Oregon coast that really serves as the main lab of this class. So a lot of times that's a motivation to take this class. Here in Ontario, Oregon, we're far away from the coast. It's a 10-hour bus ride to get over there. And every term here in the Treasure Valley, every year that I teach this course, there's always one or two people who have never been to the ocean, right? And this course is, to them, a way to get to the ocean, to go see the ocean for the first time, right? And I value that. I think that's really amazing. And I also feel humbled that I get to be the person to explain the ocean to you and then to take you there, right? So whether it's your first time or your 500,000th time to the coast, it is always a fun, adventurous experience, especially when you have a little bit of ocean knowledge in your back pocket, right? So General Science 108, Oceanography. Okay, General Science 109. This is also a really fundamental class, meteorology or atmospheric science. Meteorology is a very overlooked physical science, and I say that not in this sort of grand judgmental perspective, but overlooked from myself. Meteorology was not really something I was ever interested in. I'm not sure why. I grew up in western South Dakota, seeing large thunderheads, large storms that you could see for hours and hours and hours before they came on top of you in rain buckets, right, with huge lightning storms. But I was never really infatuated with that perspective of the atmosphere. Storms are neat. Okay, tornadoes seems really scary, but really the air is clear. I don't know if you've ever noticed that, but like There's air between you and I right now, and it's clear. I can't see it, right? I wonder if that, at least for me, was part of why I never asked questions about the atmosphere. And that's why I say this is an overlooked science. I never asked the questions, and I'm a curious feller. Okay, it wasn't until I got to Treasure Valley Community College and was asked to teach this course for the helicopter pilots in the Starhawk program out of Treasure Valley that I had to learn this stuff. Right. So the first time that I taught this, I was literally learning the material while I was teaching the material, which is like the worst way to teach a course, I have to tell you, right? I was anxious all the time. I felt like I didn't know what I was doing, all this, because I didn't really. I was just a student in that case. However, I had the value of science on my side. I was a trained scientist by that time. I could evaluate things objectively. I knew how to collect data. I knew fundamental physical principles, so all of that stuff went good, and it was a really great class. It was really fun. But after repeatedly teaching this class and learning this material, right, I have now been able to incorporate the atmosphere as a whole system of itself, which I was never really able to do before. And that was, I would say, the final nail in the coffin to me to make myself an Earth systems scientist, right? Where I now look at all these parts all together and how they interact, right? It's the interactions that I'm really, really interested in. So in General Science 109, we are primarily focusing on the fundamentals of the atmosphere. So this is not a class on like, hey, I'll train you to become a meteorologist, okay? No, this is a really basic class in the structure and movement of the atmosphere. This is in some ways, very similar to, say, General Science 106 or Geology 106, where it's just a survey of all of this. You're not going to come out being able to predict the weather, right? Like anybody can. However, there are, we can use probabilities of what is going on over there, which is where the atmospheric current is moving, that we can tell what's probably going to happen here at such and such time. So the power of looking at the atmosphere is a predictive power. Really, it's a probability that's based on conclusions and data that are derived from elsewhere. But what we spend a lot of our time in meteorology is the, first of all, the layers of the atmosphere, or this whole structure itself. As you go away from that mass of the Earth, again, the gravitational equation where the mass that is you, or the mass and the mass that is the Earth, as they increase in respective distance away from one another, the gravitational force reduces with the square root of that distance. Now, that's the same for the particles of the air, right? All those particles that you and I can't see right now, the air, those particles are held onto the Earth by the gravitational force. And the further that they get away from the Earth, the less gravitational force they have on them. So there's this natural layering that has occurred on the Earth because of that reduction of distance. So you may have heard the air is thin up there, right? There's less oxygen up at 30,000 feet, and that's quite true. Because all those oxygen particles are held onto the Earth down near the surface, right? And when we go up, and up, and up, more of those particles are below you than where you're at or above you. Okay? So layering of the atmosphere is really critical to the overall understanding of the rest of the course, which mostly focuses then on the lowest layer there, the troposphere, which is where all the action occurs. Okay. Now, one of the aspects that I really like from meteorology is bringing in the Earth, right? Bringing back in the geosphere, and also invoking the heliosphere. So part of this graph right here is showing you how the heliosphere and the geosphere interact. And there's kind of this buffer zone of the atmosphere in between. And the solar radiation that comes in during the day after the sun rises warms up the Earth. And when the sun sets, the Earth slowly releases that energy, that radiative release of energy. And that's really part of this graph right here. It shows sun comes up, Earth warms up, sun goes down, Earth cools down. Okay, and in that sense, then, every day is kind of like a mini season of the Earth, right? Where temperatures vary throughout the Earth based on solar radiation. So we're also looking then at the transfer of that heat. What happens when the Earth radiatively releases its energy? Well, it goes into the particles that are in the atmosphere. And what do those particles do with it? Well, those particles, as a fluid, air is essentially a fluid, are greatly affected by temperature gradients. Where it's hot, those warm particles are very energetic and they're diffusing outwards to where it's less energetic. So hot flows to cold, okay? Dense may flow to well, I guess less dense. So gradients are really important, and it is those gradients of temperature that really drive the weather. Now, not solely, we need to add in another critical sphere of the Earth, which is the hydrosphere, okay? The water sphere. From the oceanography class, right, just mentioned or discussed a few minutes ago, the oceans and the atmosphere are inextricably linked, okay? And it is the interaction of those two, well, and the heliosphere, giving the ocean some of that energy, that encourages evaporation. Water particles evaporate up into the atmosphere, and then they get far enough away from the radiative release of the Earth that it gets cold. And when it gets cold, the water condenses, and that forms cloud droplets. So we end up with some amount of water vapor in the atmosphere, and we refer to that most typically as humidity. The bulk of the course, then, after learning all those fundamentals, the deliverables of that course is really thinking about storm fronts, right? How is that temperature, the gradient, the movement of that temperature, and the water vapor therein, how does that affect what we call weather? Okay, this is a really, again, it's a fun course, it's an interesting course, and it's that last component of the Earth system sciences that I think is not, at least for my own case, was not all that well known to me. Although I do wake up every day and put on clothes for, whatever the weather is, right? So the weather clearly affects us day to day, but we don't oftentimes think about its processes. Okay, the energy course, General Science 110. This is an extremely exciting course and extremely important to you and I because we are high energy users, right? Right now, whether we're doing this discussion here in class and we're using this brilliant projector that's coming from my computer, or whether you're looking at this in the online format using a computer in the safety of your own home, or just some random person looking at YouTube that happened to stumble across the video, you YouTubers, we are high electricity users. Right now, everything that we're doing right now, even though it seems like we're just sitting here basking in information, you're using a shit ton of energy, right? It's keeping this building warm and habitable because it's like 31 degrees outside. I don't know, it's cold. Okay, it's keeping the lights on so you can see your pencil and paper. It's putting the light on the projector so I can point at this stuff and talk about it, right? Now, more than even just that, all of the stuff around you, the pencil that you're writing with, or pen, the paper that you're writing on, the desk that you're writing on, are also delivered to you with energy, right? These are the kind of ties that we really try to focus on in this energy class, or at least I do. That's kind of the punchline, right? Is to draw your attention to energy usage, right? That we are fundamentally dependent on the Earth's resources for this energy, and then we are high users of that. Okay, well, what are these Earth's resources, and where does that come from? Here's coal. I like to really focus on coal for quite a bit of time. I'm a geologist, after all. So I like to really discuss the geologic formation of coal, and then the production of energy from coal. Now, once we get to know that system, it's not much different for the production of energy from natural gas. Okay, it's just really burning stuff to warm up water, and then that water forms steam, and that steam turns a turbine, and that turbine is turning a big hunk of metal that's creating an electromagnetic force that's pushing electrons down a wire, copper or aluminum, all the way to you, to that power receptacle that your phone's plugged in right there, right? That's the system we're trying to look at here. In all those other courses, we were looking at the natural systems, right? Ooh, tectonics and subduction and volcanism. Ooh, mass wasting over there. Ooh, oceanic currents. Ooh, the photons coming from the sun, right? Processes of the natural world. But in energy, again, just like that question in geology, what's your relationship with the Earth? Yeah, energy is one of the courses where we exclusively focus on that relationship. So I always bring it back to the Earth, but really this is a course focused on energy. So we start out, of course, by looking at energy mathematically. It's not a math-heavy class, but we do involve heavily the variables of mathematics, right? So we're not always tangibly using numbers all the time. I will ask you to look at your power bill, or we'll find a power bill online, or you can use my power bill. So we can use raw, real numbers about electricity usage, but really we spend a lot of time in kind of the abstract concepts of the mathematics behind energy, using quite a bit of examples, because that helps some people to understand the math, but other people are just fine getting to know the variables and the ups and the downs. Okay, so what is it, and then why do we care about energy? Well, hopefully I just spelled that out to you a second ago. Because your phone is sucking the electrons out of the wire so you can text somebody. That's why we care, right? Okay, maybe it's for our phone. Maybe it's for the projection of this class. Maybe it's for, your drive home. I don't know. But we have to care about energy because we are energy driven. This is how our society runs. In fact, this is a large part of how civilization runs, is based on energy. Right? So we also do look at that perspective of the survey of energy throughout history. It's really difficult to look at energy, 10,000 years ago, clearly, but really up until about the 1800s or so, biomass, burning wood, or cow patties, or whatever, was the main source of energy that did all of our bidding. We didn't use much coal. Maybe some people did regionally, right? Maybe some people found some oil seeps and were using a little bit of that stuff. But for the most part, we just burned stuff. That was exclusively what we used for cooking and heating. We didn't have electricity. We didn't have, we didn't focus on electricity. We didn't fundamentally have at the center of our lives electricity. So this course is really, even though we do involve the survey of the history of energy, this is an industrial revolution class, right? This is talking about how burning energy-dense stuff has changed your life, right? How you no longer have like a 45-year life expectancy, and you have the access to medicine easily, probably because of energy, right? I mean, yeah, there's some good things going on up here that made that possible, but it's literally the access to energy that really makes it possible. Okay, and then the last portion of this course is how do we harness the energy from the Earth? So again, those mechanical processes of turning rocks like coal into electrons for your phone, right? How is this stuff done? This is another course. I mean, all the courses usually have field trips. I love field trips. I love going out into the wide open world and showing you this stuff outside of the classroom, right? This couple of hours that we're together once a week, this is fun. We can dance around. I can show you all these pretty pictures. Well, these ones aren't so pretty, but
None of that's really useful unless you take this out of the classroom and you go apply it to your real life. So field trips are really important, so we can do just that. We can take you out of the classroom and I can go look at rocks with you, right? You can go see rocks in their natural habitat. Well, in this class, we here locally in Treasure Valley, we have access to quite a few local power production plants. So we take a day-long field trip to go see, first of all, a natural gas burning facility, to go look at a couple of solar arrays and the energy production there. We have a geothermal facility in our backyard over in Vail, Oregon, that produces something like 20 megawatts, which is pretty neat, right? Geothermal resources are not all that common, and we have in our backyard. A hydro dam, we take a look at a hydro dam, and then also we're quite fortunate locally to have access to windmills, right? To large wind production about an hour north of Ontario near Huntington. We can go look at the Lime Wind Facility and how those gentlemen, it's a privately owned, privately and family owned enterprise, how they really took the bull by the horns about a decade ago and said, I want to create wind energy, and he's done it. And it's pretty amazing. So this class does have a field trip component to it as well, so we can look at energy production. Okay, and now, of course, this class, oh my gosh, an hour later, I'm going to finally talk about Violent Earth again? Yeah, Violent Earth, this was new, spring term 2017. This curriculum is new. This is something you're not going to see anywhere else, any other institution. Well, maybe University of Wisconsin-Eau Claire, if you guys ever, reinvent the course and do it. Maybe I'll have to come teach it. I don't know. Love to. But the idea for this course was taken from a time where I taught at University of Wisconsin-Eau Claire, and they mold around the idea of producing a kind of a sexy geology class, right? One that could get the people in. Violent Earth? Yeah, that sounds awesome. I want to take that class. So maybe that's how you got in this class. I don't know. But that's what I was going for, right? So Violent Earth, it was new in 2017, brand new curriculum. Not going to see it anywhere else. And this is what you'll spend the next 10 weeks looking at, is violent volcanism, megadeath, right? Mass extinction is another way to say that, a more proper way. And really large, giant impacts to the Earth. This is the moon-forming impact that we'll talk about next week. I don't use a textbook for this class. You probably saw that on the course materials. And those of you taking the course online, or those, again, random YouTubers that come across this stuff, there is no textbook for this course. In fact, instead, what is the text for this course is all of literature, right? I just pull the raw literature about some of these events. Sometimes I give you the pinnacle papers that were written about this. Maybe I give you sort of a synthesis paper or a summary chapter from a book. I pull a lot of different resources from our wonderful academic system, the libraries, WorldCat. I pull a lot of resources together, and it's not in one book, right? I don't have the confidence that one book could serve all of the subjects of this class, where really this is just a smattering of a whole bunch of really interesting things that I've learned through my career in education as a geologist. And I thought it would be great just to compile that all into a really fun class. So that's what we're going to do here, is we're going to use maybe a couple of papers from this special paper from the Geologic Society of America. Maybe I'll use a couple things from another class's textbook, stuff like that, right? Now, for those of you that are not enrolled, well, you're clearly enrolled, you people. But for those of you who are not enrolled in this course, there should be references for this material either on the slides or in the notes or coming out of my mouth, and you should be able to find this material on your own, okay? But really, I don't want to have a textbook. Textbooks are relatively burdensome in some cases, especially for a course like this. Really, this is more like an upper division class. you know, this isn't an upper division class. It's not going to be hard. It's not going to be painful. It's not going to be all these building concepts. But this is an upper level kind of a seminar class. These are specialty topics that you're not going to get anywhere else. So I treat it as such by giving you the raw information. Now, there is a problem there because how many people have read a scientific journal article in the last week or year or lifetime, right? You're not scientists. I understand that. And the expectation isn't to give you this reading and then for you to read it and understand it. No, 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 no. I want to look at the introduction, some of the figures, and the conclusion. And then in class, during our time together, we'll take snippets of this, we'll go through some of it, and I'll digest it for you, or I'll help you digest it, right? I want you to have access to that raw material, the details, rather than me just telling you elaborate stories like they're fairy tales, right? I want to go back to the source and to give you supporting details, supporting material, where really the takeaway point is happening right now. The takeaway from the class is happening as we're having class. It's not happening through the reading, okay? It's happening through staying engaged during class, approaching the readings, you know, seeing what you can get out of that stuff, and then coming back to class and asking questions, asking more questions, talking about it, right? That's what we're going to do here. So stay up on your assignments, review the lecture material. Okay, it's always a good idea to review the material the night after you've had this lecture, and then maybe breeze through it the 10, 15 minutes before you come to class. Right? Those are really good study strategies, and that's going to make you very successful in this class. This is not a memorization thing. Okay, this is an exposure thing. And I know that some of my colleagues out there would kill me for saying stuff like that. But really, I'm here to expose you to these wonderful and elaborate stories that aren't just stories. This is science. These are probable conclusions derived from data, right? And that's what we're going to do here, and that's what I want you to be exposed to, right? If you're here, well, here in Oregon, for an Associates of Arts Oregon transfer degree, you have to take 4 sciences. 3 of them have to have a lab, and then this one is a non-lab science. You're going to take 3 other sciences where I'm going to hammer you with details, hammer you with lab stuff. Maybe it won't be me, but the expectation for doing science comes in those other 3 lab classes. I believe that you are entitled, fully entitled, to having a survey class that exposure to these broad topics is the point, and that's this class, okay? So with that, we're a little over the first hour of class, and I want to go ahead and take a break so you can get up and go potty. You can stretch your legs. I can stretch my voice and get a snack, and then we can, let's take a 5-minute break, and then we'll come back. Also, I need to stop the video before it takes up any more memory. Okay, and we're back. We're back. Where were we? So a big portion of that last hour was like a bunch of gobbledygook, right? This is how I teach. This is what lecture is like in this class. And then all of a sudden, at the last like 30 seconds before class is out, I give you an assignment, right? I don't just talk to hear my own voice. Actually, it's pretty ridiculous. I just played a little bit of the video back during the break, and I hate hearing my own voice, actually. It sounded ridiculous. But you're paying, well, maybe not if you're not paying for this YouTube video, but why are you watching then? Sorry, but if you're paying for this class, what I want to ask you, or maybe ask yourself, what are you paying for, right? There is this perspective in academics or in degree seeking that you have to take this class. As I mentioned, you have to take 4 science classes, and this is one of them. So it's just a monkey to knock off the shelf kind of thing, or whatever the saying is. But I really want you to avoid thinking that way about your education and to really see how valuable the words that are coming out of my mouth are. Okay, not because like I'm some golden scribe and everything that I say is holy. No, I've had the good fortune and some amount of privilege, clearly, to go through my college career and to be here in front of you today and teaching, right? I understand that. And along the way, I've gathered a whole bunch of information. Okay, and it's that information that, I just want to, I'm here to translate to you. That's my job. Not as a geologist, but as a geoscience educator, is to give you all these details, to give you all this fun stuff. Some of it's fun, some of it's not. And then, to deliver that, not just to give you a textbook and to tell you the questions in the back of the chapter, that's not teaching. Okay, teaching is having the discussion with you, right? Now, the way that this class is formatted and is structured in this context, because I am making all these videos here to upload for the online class, is much less question and answer and much less interaction. And I know that that's probably going to bother some of you. And on breaks, I'm clearly very accessible on breaks. We'll even take a longer break if we want to do some questions off video and stuff like that. But we have time to engage. Okay, so during class, I know that it's going to seem like I'm hammering you and I'm spewing out all these details and all this stuff, right? But just hang in there, right? Hang in there. This should be fun. It's fun for me. I like doing this stuff, so hopefully it doesn't kill you in the process. Okay, so the last hour was a lot like how the next 25 hours is going to go in the class, right? But instead of talking about that, let's summarize that last bit. Really what we got to was I laid a lot of these little tiny nuggets about the Earth system, right? You might have thought I was just talking to myself about like, oh, I didn't like clouds before, but then I had to teach about clouds and I like them now. No, I'm trying to lay these little bits of information through kind of this narrative or through maybe story format or whatever this is, for things that we're going to use later. So I should never say something just once in this class. Now, it might seem that way sometimes when we come upon, we're talking about Pleistocene glaciation and Ice Age mammoths. And it may seem like I only discussed that once. But if you're taking notes, if you're listening, if you're reviewing the material, particularly videos, because this term you're going to have those handy for you, I lay all of that stuff down, talk about the subject, and then continue to reference back to it, okay? So all of this information should be all linking around all these different paths, and we should have, at some portions, duplicate information, right? I should be telling you the same thing over and over and over and over, but not in the way that it makes it sound redundant. Okay, I'm trying to reinforce topics that I talked about in the past. So all of those things in the last hour, they may have seemed random, but they will come back as a structured portion of the course. Okay. All right. Now, a big part of that was to prime you for the Earth system sciences. All right. Up here is a fairly good definition of what we might consider the Earth system sciences. That this is a study, science, of the interaction between the Earth's spheres, okay, between the Earth's spheres. And you've already heard me talk about these spheres before, all right, but let's write those on the screen. The heliosphere. Helios, that's a Greek word derivation for the sun god. And so Helios is in reference to the sun. The sphere of the sun is the entire solar system. Everything that the sun has within its gravitational grips, way out there on the periphery, all the way out to the Oort cloud, the sun's sphere is huge, is that big. That's what we're talking about with the heliosphere. So clearly when we're talking about Earth systems, sciences, the portion of the heliosphere that we're really focusing on is a really small portion. The portion that the Earth moves through, right? In this orbital fashion, in a really close area to the sun, right? It's only 150 million kilometers away from the sun, which another way to think about that is in one astronomical unit. That's a unit that we use to talk about interplanetary space, where Saturn is 29 astronomical units away from us, somewhere around there, right? So Earth occupies this portion, this small little portion of the heliosphere, where there's a lot more to it, okay? All right, enough said about the heliosphere. Hopefully you get a good understanding of that. The atmosphere is the gaseous phase of the Earth, is how I prefer to think about it. It's not the rocks, it's not the water, it's the gases. So you right now, well, maybe not because we're in a building, but when you stand outside, you're standing on the interface between the sky and the Earth, right? You're standing on the geosphere, and all the way around you, you're immersed in this liquid that is the atmosphere. And that extends all the way above your head, right? And up into what we call the exosphere, right? The highest layer of the atmosphere. Now, that is a very thin veneer around the edges of the Earth, right? We're only talking about 80 kilometers to that threshold, to what we would refer to as the exosphere, as things that are beyond. So really, 80 kilometers, that's, what maybe the distance between here and Mountain Home or Boise, right? If you're elsewhere around the nation, then look up what 80 kilometers is between you and the next place away. But 80 kilometers isn't a great distance at all. But to us, going lateral distances seems okay, to drive for hundreds of miles or hundreds of kilometers. But to go up or down is a pretty big deal. And really, you don't have to go up all that far to get, not out of the atmosphere, but into a place where the atmosphere is much different than the place that you're standing today. Where, on the contrary, if you travel laterally around the Earth, or what appears to be in our plane right here on the Earth, you pretty much see the same conditions, right? I mean, maybe climatic conditions change and biomes and stuff like this. But my point here is, again, the atmosphere is this stuff. It's from your interface where you're standing on the geosphere up there, right? Until you get to the cold vacuum of space. And arguably, there's no end to the atmosphere, really. Because the atmosphere, these gaseous particles are held in by the Earth's gravity. Okay, well, the moon is held on by Earth's gravity. So is the moon in our atmosphere? Well, if you're a meteorologist, hell no. If you're an Earth system scientist, maybe, right? So some of these definitions and these interactions really depend on your perspective, on how you're coming at this problem and from which discipline. And that is a scientific problem from making disciplines. You understand that we've made this perspective problem, right? The question is not irrelative, but the question is made up out of our own boundaries that we've made for ourselves so we can study individual disciplines. Okay? That's how science has been done for a couple hundred years, is to make disciplines and then to focus on those disciplines. And we're still going to do that. That's great. But now the need arises that that's not enough, that we have to always be thinking about the atmosphere while we're thinking about the heliosphere. Okay, it's all the systems interaction. Okay, then hydrosphere, that is the water hydro, the water sphere of the Earth. And this is mostly the ocean, because that's where most of the water of Earth is contained, but there are the rivers and the lakes and the streams, the other water that you're familiar with. But don't forget about the frozen water, the cryosphere, the glaciers. Don't forget also about the gaseous water, right? The water that makes up the humidity of the air, or the water that's up there in the clouds that falls as precipitation. That is all part of the hydrosphere in the atmosphere, right? So you see that there are these very clear areas where the systems become intertwined. Forever, meteorologists have been focused on that, that system, right? So it's really easy for that to be integrated, the hydrosphere and the atmosphere, where some other of these connections between disciplines or spheres have been a little bit harder for scientists to, well, I don't want to say scientists specifically, but just overall the discipline of science, scientific knowledge, to come to these really focused interactions. Okay, so the hydrosphere includes all water, right? That also includes the water that's within the Earth, trapped in the Earth's mantle. Yeah, the mantle of the Earth. I don't think I ever actually pointed this out very clearly, but this is kind of like my gimmicky diagram of the Earth. It's clearly not to scale with these gigantic clouds that are half as big as the Earth's core. But anyway, here in green is the Earth's mantle, mostly made of mineral olivine, well, until it gets under pressure and then goes through all these different metamorphic transitions. But my point here is the mantle actually contains a whole lot of water. As these subducting plates subduct into the mantle, they carry with them water from the surface. And I'm not talking about free floating water either, not like there's a bunch of liquid in between the rocks. This is sometimes, most of the time, water that's trapped in minerals. And so that water is trapped in the minerals and goes down with the plate. Now, this isn't a crucial part of today in this class, but just to lay that down for a second, it's actually that water that goes down into the mantle, and about at 100 kilometers or so in the mantle, that water is driven off. It's hot down there, right? So that water, you know what happens to water when you heat it up? It turns to steam. Well, similarly, this water that's trapped in the mineral phases, okay, minerals like muscovite, that water dehydrates or decouples away from that mineral. So it dehydrates and that goes into the mantle, which lowers the melting temperature of those rocks, kind of like putting salt on a snowbank or on ice, lowers the melting temperature, so it'll then turn back to water. Okay, similar process, it's called flux melting, and that creates the molten magma, that eventually comes out of a volcano. So back to the hydrosphere. The hydrosphere is actually largely responsible for the process of volcanism. Boom, right? Amazing. These are maybe interactions that, your average Joe, we're not really thinking about, okay? But these are interactions that have become very clear over the course of scientific study. Now, geologists have focused on flux melting for a long time. Meteorologists, not so much, right? Maybe water they know is emitted from volcanism. And geologists aren't really focused in that hard rock sense on what happens to the water once it leaves the volcano or how it gets down there. Now, in the Earth system sciences, we are concerned with that, right? And I'm not trying to make blanket statements about geologists only think about rocks and meteorologists only think about clouds. But typically in our disciplines, the bubble of knowledge is only pushed by thinking specifically about your discipline. Now here, in the Earth system sciences, we're bringing it back down and really trying to look at the connections between all of them, and then those connections become their own bubble of knowledge, their own pushing, called research. Okay, now, not all of the water is dehydrated from this plate into the mantle. A good portion of it is, and not all that water goes out the volcano. Okay? Some of that water remains trapped in the mantle wedge, and then some of that water just never dehydrates. It keeps going down with the plate to a layer called the D double prime layer. Okay, I don't want to get too geology on you now, so let's skip out of the hydrosphere. But a big point there is to understand that the hydrosphere is within the mantle of the earth, comes out of volcanoes, it's in the ocean, it's in the air, it's in the lakes, it's in the rivers. Oh my gosh, it's everywhere. It's in your body even. The hydrosphere is everywhere. Okay? And this may be a critical component to the functioning of our Earth system, is the volume of water and the temperature at which water, the temperature of the surface of the Earth that allows the range of temperatures for ice, water, and vapor, right? That trinity, if you will, of water. So that's why we have the saying, right? Water is life. I don't know if that's a saying or if that's like a statement out of the Standing Rock protests, right? Is where I became very familiar with that. But water is life. Water is very critically needed for what we think of as life. So the hydrosphere, then, hopefully you have a new, greater understanding of that as well. The geosphere, now this is the discipline of geology, geology. The geosphere is the hard rock sphere of the Earth. So that's this all the way from the crust, the broken up round plates of plate tectonics, the mantle, the outer core, which is liquid, and then the inner core, which is solid. Both of those areas of the core being made of nickel and iron crystals. I guess when it's solid, here it's liquid. The geosphere, then, is a really, I think, tangible sphere. Maybe that's because I'm a geologist to understand. Okay, the atmosphere, pretty easy to understand. Maybe not its limits, or it's all of its composition and stuff like that. Same thing with the geosphere. It's tangible. Okay, I get it. The Earth is a big rock. I'm standing on it. There's the geosphere. Okay. Now, just like the others, that maybe I took a little bit too long to go into detail, but just like the others, the geosphere is a system. This isn't a static rock. It's not just sitting there being dumb, right? I mean, not that it's like sitting there being intelligent, but it's not just sitting there doing nothing. Okay, the Earth is dynamic and is moving, right? I don't know if you've ever been in an earthquake, but the Earth freaking moves, man, right? It doesn't just have mass wasting and rivers and floods, but it has volcanoes and earthquakes and large temporal time movements, okay? Where over the last 200,000 years, the Atlantic Ocean has opened. There was no ocean there before, okay? That's, so what I'm saying here is the geosphere is just as dynamic as the movements of the atmosphere that create weather, the hydrosphere that, again related to weather, but also your lakes, your rivers of moving water or groundwater, and the heliosphere, the moving heavenly bodies, the planets, right? All of these things are dynamic. None of them are static. And clearly, the most easy for us to see, I think, because we are part of this, is the biosphere. To see that that is not a static entity. The biosphere is completely animate, right? I mean, no holding anything back here. That's kind of what defines the biosphere to us, is animate, right? Things that are living, things that are moving, things that are breathing, things that are eating, things that are fornicating, right? Things that are doing what life does. That's the biosphere. Okay, now, the biosphere isn't just individual creatures, it's an ecology, right? This is all of the carbon-based life forms around the surface of the Earth and in the Earth, right? We now know that there's more, by mass, life living below the surface of the Earth than there is above the surface of the Earth, complete with all your microorganisms and thermophiles. But my point here is the biosphere is a critical component of the rest of all of these as well. As organisms, oxygen-respiring organisms like you and I and wolves and salamanders, we need oxygen to make our little fires in our bodies with sugar and make little explosions, little pistons to make our arms move where we wanted to move or make our brain function, right? Oxygen is a fuel that is incredibly important for us. And oxygen, where do we get it? From the air, from the atmosphere, right? So water, also critical for the biosphere. Minerals, or what we think of as nutrients, critical nutrients, are derived from the geosphere. For us, as a pretty complex organism in the food chain, right? We don't just get stuff from the rocks like lichens do. We have to wait for those lichens to be eaten by stuff and for all those nutrients to work their way up until they can get to something that we eat and we get the nutrients, right? It's a complex food chain. And then also the heliosphere, even sort of more rudimentary than the lichens, and to a certain extent the lichens, we can't just sit here and gather energy from the sun like the plants do, right? They're animate, they're living, they're part of the biosphere, but they're a little bit different in that they can use the sun's energy to make those sugars that then some other thing eats and then we eat, right? So we are connected to the heliosphere as well, even as, oxygen respiring organisms, where those plants, they are carbon dioxide respiring organisms, right? They need to breathe in through their stomata carbon dioxide, to combine that with water, using the sun's energy to forge that stuff together into that process of photosynthesis, and then they create those sugars. Okay? So what I'm really trying to get to here is to underline, I went through all those classes before, right? It might just seem like, oh, there's stuff to learn, there's classes. But this is why, right? Is the connection between all of these spheres is Earth system sciences, and we're not going to leave that alone in this class, right? That's not something I can just lay on you on the first day and never talk about again. This stuff should always be in the background. And we have the good fortune in such a survey class, Violent Earth, to talk about these interactions, these very specific interactions that have to do with all of these spheres. I think it's really cool. Okay, so we'll go on from the Earth systems sciences, and that will, of course, come back day after day after day after day, and by the end of today as well. Okay, this slide, back to the blue marble. I have a little zoomed in version here. This is from the Aaron's textbook. I think it's called Introduction to the Atmosphere. And it's a meteorology textbook. And I like this to include this picture because it really shows that thin veneer of the atmosphere, how really thin the atmosphere is compared to the rest of the Earth, the geosphere. Again, back to the blue marble. The Earth can be in one picture, right? In one picture. The Earth is one thing. It's finite then. It's not infinite. There's not infinite Earths. There's not even two. There's one Earth. One finite Earth. And that Earth is complex. And it has these 5 main systems that I've outlined that are all working together. Not like they're all happy, joy, working together, making a party, but they're all working in such a way that this system is a system of systems. Wait, no. The Earth is a system of systems then, right? All that are working together in sort of a form of checks and balances, right? One thing changes here, and that, of course, has rippling effects through everything else, and everything else changes slowly. And those changes, of course, make other changes. Like the chaos theory, right? Changes make a new foundation for more changes, and then the results based off of that change are inevitably, inextricably linked by the changes from the previous change, right? Or the solutions from the previous change. Okay, that might be a little bit out there. But my point here is that the Earth is finite, for one, and is also very complex. Okay? You can put it in one picture, but it doesn't mean we understand it. It doesn't mean that it's simple. It doesn't mean that you go in one side and out the other, right? This is a complex thing. It's not a machine, and it's not an organism. It's an earth. It's a planet that is alive. Okay? Not maybe alive in the sense as in I'm alive, that I have a brain, and I have lungs, and I can do this, right, or that. Maybe the earth can, I don't know. I haven't seen it before. I doubt it. But the earth is alive in the sense that it has a biosphere that works in connected ways with the rest of the spheres. Okay? Seasonally, the earth breathes in some way not like we breathe, but that's our closest word for it. In the fall, or excuse me, let's go to the spring. In the spring, when all the trees are budding, and all the flowers are blooming, and all the rabbits are making babies, okay, well, the rabbits don't have a ton to do with it, but all the plant life is re-emerging in the northern hemisphere. All that plant life is photosynthetic. So what does it need? Sunlight, got it. Water, got it. Carbon dioxide, aha. Where does it get it? It sucks it in from the atmosphere. So in February, when stuff in the northern hemisphere is not living, carbon dioxide levels are pretty high. In May, when green things are trying to suck up all the carbon dioxide levels are low. Okay? Well, then what happens in the fall? When everything dies, all the leaves fall off the trees, all the flowers are dead and gone, all the herbs are composting back into the soil. What happens to that green stuff? It turns brown. It oxidizes in the presence of the atmosphere, and that carbon turns to carbon dioxide, and all the Earth's biosphere exhales again. So the Earth has, we call it breathing because that's anthropomorphism, right? But it really does have this cycle of gases that are not unlike our own lungs on a biannual basis, right? It's amazing and it's complex. The Earth is a system and it's alive in some way that we don't really understand. Okay? Again, not to anthropomorphize the life. The Earth isn't alive like you were alive, or like a gazelle, or like a microorganism underneath my feet. The Earth is alive in a way that we don't tangibly understand, but we know that it's not alive, right? That wouldn't make sense. It's a system that's all working together, and our closest analogy for it is like a body, how it all works together. Your digestive system works with your nervous system, works with your circulatory system, works with everything else. Okay? It all works together, not in perfect harmony, but it works to work. It does it. Okay? And if you still are, skeptical, which again, remain skeptical, that's fine. I'm not here to make you non-skeptical or to tell you can't be. But if you're still skeptical about this, go out tonight and look at the stars, right? You are the eyes of this world, right? I didn't say that. Rob Hunter said it, Grateful Dead, right? Song called, what is that song called? Oh yeah, you are the eyes of the world. And that is a fundamental truth, that you, as a living organism, and this sentient conscious being of humans, we are the first thing on this planet that has the ability to look off of the Earth. I mean, not to say that deer can't look at the night sky. Okay, fine, they look at the night sky, but they're certainly not making constellations out of them, and they're not using telescopes to look at Mars. Okay? What I'm talking about here is that you are a portion of this live Earth. You are the planet's eyes out into the cosmos. Why you, or why us as humans? Because you're made of this earth, right? Nothing in your body, nothing that you're drinking right now, or no any of the snacks that you just ate during the break, or any of the poop that you'll be defecating into the toilet is disconnected from the earth. It's all derived from the earth. You are made of earth stuff. Your mommy, when she made you in her womb, ate food from the earth that built you from a tiny zygote up. You are made of earth, and you have eyes to look at space. Okay? So the earth isn't alive in the same way that you are alive, but it is undeniably living. Okay? That can go on a very long conversation. It's very interesting, and I would, for reference for that, part of this conversation and part of those details come from a book called Earth in Human Hands by David Grinspoon. He's an astrobiologist. He was actually here last spring for Earth Week. If you were here around Treasure Valley Community College in Earth Week 2018, David Grinspoon was kind of like the keynote lecturer on Earth Day. He was here. He was over in the Cultural Center, and he spoke to a crowd of a couple hundred of us here in Ontario, talking about his book. And in that book, he talks about this perspective of the eyes of the world. I mean, not just from the Grateful Dead point of view, but from that point of view that I was just speaking about, which comes from, well, not comes from, but is related to this idea that I'm talking about of Earth system sciences, which has its root in something called the Gaia hypothesis. Okay? So there's a chapter from his book that will be the main reading for tomorrow's or for the next day's lecture. And not that we're going to focus on the Gaia hypothesis very much. It'll come in and out of this class just as Earth system sciences will. But I think that chapter of that book lays a really good understanding of how the Earth systems are working together, which was why the pioneers of that hypothesis, Lynn Margulis and James Lovelock, why they came up with that as a hypothesis was looking at all of these interconnected systems, right? And then trying to describe that in some way. So Lynn Margulis was a biologist, a cellular biologist, I think. And then James Lovelock is a physical chemist. So they're taking two different disciplines and kind of looking at them together to come up with a different way to look at the world. Okay. So Earth system sciences, again, these different disciplines where we have different perspectives. Over the last couple of decades, each discipline has, in this very educational type of format, right, of what are the 5 takeaway points kind of way. All of these disciplines had narrowed down these big principles for their science. So 5 principles, meaning that if you take a class in meteorology, here's the 7 things that you should learn. The 7 things that you should know, whether you're going to school in Oregon or in Massachusetts or in Hong Kong. These are things that all meteorology instructors should be making sure that these are objectives and deliverables for their students. Okay, so this is all, this is an academic discussion on how to teach effectively, and this is what each discipline came up with, was the atmospheric science literacy principles or the climate literacy principles. Okay, all of these principles, each discipline derived. Okay, well, okay, that's great, right? That's awesome. Actually, I've used the Earth science literacy principles, the big ideas of the Earth sciences. I use those a lot, and I love those videos on YouTube, right? If you, in fact, while you're reviewing this, go ahead and put that in YouTube. The 9 big ideas of Earth sciences, and these really great videos from the American Geosciences Institute, AGI, come up. And they're well done, and they summarize really well what I, as a geologist, when teaching an introductory class, expect to deliver to the class. These fundamental principles, like the Earth is 4.5 billion years old, or humans depend on the earth for resources. Okay, these are fundamental principles that every person who's taken a geology class should know. So this gives us, as instructors, a way to reference between each other. If we're not going to use the same curriculum, as we never should, right? I'm my own instructor, Janine is her own instructor. She does her own thing, right? But we do agree as geoscientists that these 9 things are fundamental takeaway points. Okay, is that enough though, right? Is it enough that every discipline has their little silo, their little tower, and they say, these are my principles, right? No, not at all. This is Earth system sciences that I've been shoving down your throat for the last couple minutes. So of course, what then happened to all of this stuff was this was combined together. I wish I could remember the gentleman's name. I can't, forgive me. All of these were combined together to come up with 5. You can count them on one hand, 5 bigger ideas that found the common thread between all of these disciplines and all of these ideas and wove them together into the 5 fundamental principles that underlie the physical sciences or the earth systems sciences. Okay, so again, here's all the classes that I just went through earlier. Energy has energy principles. Geology, the earth science principles. Meteorology, and atmospheric and climate. Ocean literacy principles. The hydrosphere. Earth and space science core ideas, right? Astronomy. If you combine all of those together, you get these bigger ideas. This is called the rainbow diagram because it clearly it's color coordinated by these concepts that then feed into this master rainbow diagram here, right? So it's these fundamental bigger ideas that are going to underlie all of the earth system sciences that we bring into this class. Okay? So I know I've said that a couple of times, but here's what I really mean. In this class, we're talking about violent earth. Events that have happened throughout history, well, prehistory, earth history, that have been really big and catastrophic to the earth. I've cherry-picked from a lot of these big catastrophes to promote to you those that have a really good example of how all of the spheres work together in some way, shape, or form. And again, I don't mean work together as in some sort of intelligence of, say, the snowball Earth hypothesis, that all the systems work together to get the Earth out of snowball. No. I don't mean that there's any sort of drive or sentience of what's happening here. Working together as in that's just what they do, right? It's just working like parts. And we're going to take those main events that I've cherry-picked to show the inner working between all of these systems, and then we're going to use these principles, these 5 big ideas to apply to those, right? To really drive those things home, I think, to make those these stories make sense, or to make those data make sense. We're going to be able to bring it back to these bigger ideas. Okay, so there's going to be a lot of this going on, a lot of big ideas, and a lot of up down the ladder. Okay. Sorry, I'm trying to be too silly. If you find that silly. Okay, so here we have the bigger ideas, these themes that do underlie all of these concepts in this class, and write them down. Okay, if you didn't already read that before, and I see a couple of you that are already good note takers that are writing stuff down. Okay, a couple of you, sorry, I don't mean to point you out, haven't taken a lick of notes. Right, and I'm really serious. You have to write this stuff down. It is notes in class that are your reference for this material, right? Yeah, you can look at my slides. Yeah, you can look at my reading. Yeah, you can look at the video that's here. That's just me talking, right? But what you're not doing is writing your interpretation of all of this stuff if you're not taking notes. So take notes, jot down stuff, if anything, This isn't a note-taking class, but I would love, if you don't know how to take notes, you don't know what to do when I say take notes, let's talk about that, right? Because there is a skill to taking notes, and it really helps, right? There's multiple ways in which something becomes filed in our brains. You can hear it, okay? You can see it as it's written or as it's on a picture. You can, I don't know, feel it. Can you feel it? I can feel it. I can feel this information. But there's also that recall perspective, right? Of seeing something that's in your own handwriting and allowing your brain to put yourself back in this instance right now, right? And that's what happens through writing in your notes, right? Is you're allowing your body to be your mind to be transported back to this moment. So do take notes, and don't mean to single you out, right? But write this down. If it looks like most of you are done, you've written down these principles. Let me just, while the rest of you are finishing up writing these, let me go through all of these and just say them in words. This has been said that the earth is a system of systems, and the flow of energy drives the cycling of matter. Okay, let's break that down a little bit. Flow of energy. Okay, again, remember earlier I talked about gradients. Heat gradients as the radiative energy of the earth is being released during the night when the sun is not shining, and that creates a gradient, and that gradient allows flow from high to low, or in this case, from warm to cold. And that flow of energy isn't happening by just energy flowing. It has to happen through matter. So the way that gradient is evened out is by actual matter, little particles, the atomic particles of the gases, to carry that energy, right? They start out here where they have a lot of kinetic energy, they're all vibrating and they're bouncing and they're going really fast. And then as they move away, I mean, they're not exactly like that, but as they move away from the source of the heat, they're taking the heat with them. Okay? The energy doesn't just go away. The masses take it away. Those particles, the energy that's riding on those particles is taken away. So it is the flow of energy, the gradients, that are driving the cycling of that matter. Now, why is that important? Okay, it's the cycling of that matter that's wind, right? That's what we call wind, is the flow of the atmosphere across gradients. Okay, now not every little gentle breeze is exactly like that. The atmosphere is complex. It's a fluid. It's got all kinds of stuff going on. But when think of a storm, a big storm, that's on its way, a front, you might call that. And just before that front comes, and there's that big gust of wind, and all the papers, all the dust goes up, right? And the umbrella goes away. I don't know. Right? I'm trying to paint a picture of a gust of wind. And you've probably all experienced these things, or maybe if you're from the Midwest, like I am, it blows. It blows, like my mom says, 9-0 all day long, right? The wind blows. And why does the wind blow? The wind blows because of gradients of temperature. Okay? And what is the wind but particles of gases? Okay? So the flow of energy drives the cycling of matter. I gave you an atmospheric sphere example, but we can take this example to all the other spheres, right? So just one more quick one. The flow of energy from the sun across space, right? It's produced at the sun, high, and there's not much out there near Pluto or the Kuiper Belt, so that's low, and it's the gradient that is the solar wind, right? Plenty of other examples. Now, third big idea here, that life, including human life, including our own life and your life, influences and is influenced by the environment. Okay. Now, both of these are really important here. And it is also important that they put humans into this because we are part of this system, right? The Earth system sciences. We influence our environment clearly. When we came into this room before class started, there was nobody in here. So the composition of the atmosphere in this room was like the ambient composition of the rest of the building, whatever's coming through the HVAC vents. But as we've continued to sit here and to be in this room and to maybe perspire a little bit, I know that I've got a little stuff going on there, or I'm spewing all this water out of my mouth as I exhale, and all the carbon dioxide and all the pheromones that I'm releasing, right? We have fundamentally changed the composition of the atmosphere in this room. Okay? We have influenced this room's environment. Okay, now is that the environment? Yes, right? That's this environment, but that same example can be extrapolated to the broader, the much more broad environment. Okay, like say, y'all know what I'm going to talk about here, climate change, right? Anthropogenically caused climate change, as in the emissions, carbon dioxide and methane, other greenhouse gases that have been exported to the atmosphere out of our tailpipes. Well, not just our tailpipes, but many other processes that produce these greenhouse gases that we are responsible for. Okay, burning coal, burning natural gas, primarily for producing electricity, or burning gasoline for our transportation systems, or even down to the agricultural processes. And I'm not talking about tractors, but maybe talking about cows, right? The methane releases from their burping as they're digesting material. Okay, all of these things, whether it's cows or humans, are influencing their environment. Okay, I hope that's clear. And then we are, in fact, influenced by our environment. I think this is an easier one to understand. As I referenced earlier, I do wear clothes, clearly, right? They might be dorky clothes, but I wear clothes, okay? And those clothes were, besides like the whole social aspect of why I wear the clothes that I wear, those clothes were chosen today because it's cold. Right? I'm wearing a sweater instead of a tank top because the environment influences me and it's cold outside, right? So the environment around me is influencing me in a temperature gradient, but also the environment is influencing me in many other ways too, right? It's influencing me by the surrounding ecology, the surrounding landscape, that it's relatively flat here. There's not a lot of topography. In radioactivity, there are small amounts of radioactive materials all around us at all times, and those radioactive materials are producing particles that are flying across space and interacting with your and I's body. Okay? So we are influenced by the environment. I think that point is clear. All right, physical and chemical principles are unchanging and drive both gradual and rapid changes in the Earth system. Okay, this is kind of a wordy one, but I guarantee you each one of these words is placed in here because it packs a heavy punch. Okay, maybe except the prepositions, but those are necessary to make the whole thing make sense. So physical and chemical principles. Okay, those two disciplines, physics and chemistry, are these fundamental disciplines that inform the rest of the sciences. Okay, biologic organisms are chemical organisms. We are made of organic material, carbon and hydrogen and nitrogen and sulfur and phosphorus. So we're made of chemicals, but the way that those chemicals are put together and the way that we can stand upright on the earth are physical principles. Okay, so that's just a short example on what we mean by saying physical and chemical principles. Okay, that's just the stuff and how the stuff interacts with each other. They are unchanging. Unchanging? What do you mean unchanging? There are interactions of matter, compositions of matter, rather I should say, like the atoms, the protons, the neutrons, the electrons, the bonds that they form with one another, and what is inside of them when you break them open, that are unchanging. They are what they are. Yeah, they maybe divide into smaller pieces when something catastrophic happens, gamma rays, and they combine into larger materials. That's not what we're talking about as far as changing. The fundamental particles are unchanging or remain the same. But it's more so not the stuff itself, it's the principles. The principles that something that has a negative charge, like a chlorine atom, what that means is that it has a surplus of electrons, so it has one extra bit of negatively charged stuff, and say a positively charged ion or a cation, like sodium, that has a deficiency of electrons, so it has too few negative particles, so it's overly positive. The fundamental chemical principle here is that those two things bond together. They bond together by an ionic bond, right? That they end up trading that electron back and forth and are bonded together. Okay. Physical principles, say like gravity, like the gravity equation that I've mentioned and that we'll work with a little bit next week. That is an unchanging principle. The variables are there, and what changes is the outcome, right? You can change the radius, you can change the masses, and the outcome will change. But what doesn't change is that principle itself, that the mass is always related to gravity by the radius or by the respective distance from that object. Okay? And then those unchanging principles like gravity and chemistry drive both gradual and rapid changes in the Earth system. So it's going back to that drive word that we saw over here, drives the cycling of matter. So we know what drives the cycling of matter, that's the flow of energy. But what drives changes in the Earth system? So what drives the changes of, say, the salinity of the ocean, right? It's the matter. It's related to this. But it's the physical principles that underlie this second principle, right? These unchanging things that are kind of the how, right? How all of this stuff happens, okay? So this is, again, it's a wordy one. There are very specific points that are in there, and each one of these they're not dovetailing with the last one, they're not duplicating the last one, but they are complementary to the principles before them and after. Okay, then the very last one here, I like this one a lot. I like maps, but to understand time and the scale of space, models and maps are necessary. So again, these principles here, these aren't just principles of facts, right? Of the Earth is 4.5 billion years old. That's a great big idea that you should come out with in knowledge in a geology class. But also, the knowledge that you're gaining in a geology class is the practice of asking the questions, right? So you get to know the stuff, the processes, but then you also have to get to know the process of doing so, right? A scientific inquiry. So we see that very much in this last principle and how that relates to the bigger ideas here, is that we're human, right? We are a part of this system, but what we try to do in science is to stand away and to be objective of all of this, to be something that's separate so we can study it, right? And we can study it clearly as if I don't have anything to do with that. And to do that in its best way, we have to create models, whether those are computer models to run algorithms, or whether those are models like this Earth. I guess it's kind of a map that's inlaid on a model of the Earth, right? But the model here is the round globe, and the map is a tectonic map that's laid on this to see all of the rock relationships around the Earth. So this is a good example of both a model and a map. Now, why is this necessary? Why would we say that? That it's necessary to understand deep time and the scale of space. It's necessary for you to make maps. Okay, that's not, as I said it there, it's not just some sort of, pompous way to say your brain is too small, you must have this. Well, okay, maybe it is. Because our brain is too small. Our brain, if you've ever noticed this, is actually human-sized, right? Our brain is not Earth-sized, okay? Our brain can't really comprehend the size of the Earth or the vastness of interstellar space unless we make a model, okay? Unless we scale it down into a digestible piece like this globe here. We've taken the whole Earth, the whole, 6,700 kilometers to radius, and we've taken it down to a radius of like 8 inches. So we can fit it all in one scope of view, and we can understand it. Go back to the blue marble picture at the beginning of class, right? Okay, right? That helped us for the first time in history for us to see the whole Earth all together. That was like a map or a model that helped our human brain go, click, it's all connected. Okay? South Africa and Australia just around the corner from each other, and then the Canadians on the other side. Wow, it's all the same thing. Okay? So that's where this principle comes in, is this is for us to be able to do this, to do science with these large, big things, or these really long time periods, like millions of years. We have to have maps and models and scale to make it digestible for us. Okay? Time, for instance. Time. We're going to talk a lot about deep time in this class. Okay? And that's where, of course, where we're going next, if you remember back to the first slide. Okay? Oh yeah, syllabus slide. Okay? A lot of you are probably wondering, is this like the second day of class because I missed the syllabus thing? The syllabus is posted online. If you need me to print one for you, I'll print one for you. Just let me know. But it is posted. It's out there. So review that. Okay? And it's really basic. It's really straightforward. If you have any questions, let me know. But the things that I want to point out here today, so take your own time to look at kind of like the syllabus gobbledygook and the topics, the tentative topics here. But what I want to draw your attention to are two things. First of all, the learning objectives. First thing, explain the interrelationships of the solid Earth to the other Earth systems. Wow. We've almost completed objective 1 today, right? How many times have I said Earth system science, right? So that's part of my learning objective in this course, is that you have and can explain the interrelationships. Then the second one here is to demonstrate knowledge of the geologic time scale in big events. Okay, next we're going to talk about the time scale for about 10 minutes. And then for the rest of the course, we're focusing on time and taking our events in context of that time. Okay, that'll become more clear, hopefully. Then demonstrate knowledge of regional geology. Okay, this one's a little bit interesting. We're not taking a field trip, darn. But I want to use fairly local examples. By local, I mean like Western North America. To use these regional, local examples to talk about some of these events, right? When they're relevant. Now, there's a lot of these things, these big events, that don't have any local impact, and it would be like a really stretch of the imagination for me to focus on local stuff, so we just won't. But through this class, if this is your only geology class that you ever take, and you spend your rest of your life in the Treasure Valley, you should have, by taking at least one geology class, should have been exposed to something about your local geologic setting. Okay, and I'll try to tie that in through these big events. Okay, it'll be kind of sly, but we'll get there. Okay, so this learning objective will come from a very specific assignment It'll come week 4 or 5 or something like that. All right, and then the last one here is to show written understanding of the earth science literacy principles and objectives 1, 2, and 3. Okay, now, didn't I just say learning objective, or basically did I just say that learning objective 4 is learning objectives 1 through 3, but there's a slight difference here. Explain, demonstrate, written. Okay, so demonstration comes from conversation. It comes from your questions. It comes from your comments online. It comes from your inquisitive looks every now and then. Demonstrating means just that. You have to demonstrate to me what you know. That's not always going to be in the form of a test or a quiz. Okay, in fact, we'll get to the grading policy next, or the grading basis. But examinations are not the best way for you to show me that you're learning this stuff. All right. So demonstrate that to me through other means. Right. I'll make that time available for you to demonstrate this stuff, but you are your own student. You have to do this. You're the one trying to earn the grade here, not me. I'm not going to pull your teeth to demonstrate that you know this stuff to me, right? I have, well, we'll talk more about that at another time. Okay, so writing, I want you to be able to clearly write to me as well in some essay questions. The first assignment, it'll be about these earth science literacy principles. You'll get plenty of time to write as well, but I place a lot of emphasis on these 3. So let's go to grading basis. Your grade in this class will depend heavily on your attendance, participation, and engagement. That's how I'm going to get to understand these 3 learning objectives, right? You have to show up to class. There's no textbook. This isn't one of those classes where you can just, I'm a great student. I'm super good at math. I don't need to come to class for you to doodle math on the board when I can do it in the book, right? This is not a class like that. There are subjects, and I teach some of these subjects, where it's okay if you spend a lot of your study materials with the book, where lecture is a recapitulation of a lot of stuff that we're going through in the reading. That is not this course. In this course, this time that we have together is the time of the course. This is your homework, is your attendance. Okay, take this seriously, show up to class, and let's participate and engage. Okay, so my grading basis here, I have an A, a B, and an F. That's all I'm giving out. A's, B's, and F's. Okay, maybe like a plus or minus sign here or there when warranted, but really, that's it. A's, B's, and F's. I'm not going to mess around with C's or D's. You either made it or you fundamentally did not. So let's see what you need to earn an F. If you want to earn an F in this class, right? If that's what you're after, and I mean, that's what you do in other classes, right? You earned an F. If you ever failed a class, you earned it. It's not because the instructor's an asshole. It's not because you're stupid, right? It's not either of those. It's because you simply did not apply yourself in the way that was asked of you. Okay? A failing grade is an earned grade. And the way to earn that grade is to not come to class and to not do the work, right? Not engage during class, does poorly on exams and quizzes. Okay, well, then how do you get an A or a B? Clearly, you want not an F if you signed up for this class. I guess that's not super clear because people do fail. But if you paid for this, be here, right? Take your A or your B. So I will say the majority of you will earn a B in this class. It's not going to be an easy B, right? I'm going to make you do work. I'm going to make you demonstrate to me. I'm going to hold you on the edge of your seat so you still pay attention to all of this stuff, right? Hopefully, ideally. But to get a B, come and be engaged, pass the exams and the quizzes, just pass them, right? Demonstrate a modern understanding, and sorry, actually I should cross this last thing off, which is the field trip option. Okay, this term we're not doing the field trip option. Shouldn't even have mentioned it. Then to earn an A, there's a slight difference here. You engage in class, excel on the exams and quizzes, demonstrate clear understanding. Okay, so there's two things there, demonstrate and show me on an exam, right? And what separates the A from the B appears as it's just excelling on the exams, right? No. You also need to demonstrate a higher level than your B peers, right? Or the peers, the people who are earning the B, there is a clear division of folks that are really digesting this information well. It's not just that, it's craving the information, that you're seeking out more, you're seeking out your own answers, you're asking questions, and that in itself is going to make you excel on the exam. So really, it's doing it first, and then you get rewarded by a good examination grade, and then that earns the A. I hope this kind of is clear. This is probably not what you've seen in other classes, right? Other college classes, or certainly in other parts of high school or something like this. But I don't like grades. I don't like grades very much, right? Grades have overtaken our brain in some way that if you get a C on something, people punish themselves. Oh my gosh, I've seen tears, I've seen fits. I've never gotten a C in my life, you know, this kind of stuff. But if you got a C, it's because you earned it. Again, it's not because I'm being a jerk to you that I want you to get a C grade. It's because you clearly demonstrated that you didn't understand that concept, you don't remember what that word means, or you chose the wrong answer out of these answers. One of them is right. That's multiple choice. Okay? So because grades have just sort of taken over your brain in some cases, I need to get an A, I need to get an A, I need to get an A. I want to take that away. That's not why you should be here. That's not why I'm here. I'm not here to deliver people A's because they're good people and then deliver people C's because they're bad people, right? I'm not here to deliver the grades. Of course, that's part of my job, and I need to assign those to you. And this is the grading scale in which they will be based. I'm not here for that, though. I hate that part of my job. The part of my job that I love is talking about the earth and sharing my passion with you for the earth sciences, and then getting to deliver all these little pieces that I've gathered along my way, right? That's what I love, and I want you to take that away, okay? Because it's this conversation, it's your knowledge of the earth system sciences and any little bit that you pick up from this that's going to come back to you in 10 years. I don't think that you're going to care whether it was an A minus or an A in 10 years. You passed the class. You got the degree. It's meaningless, except in the very short term, so you can get into the next college or the next program or whatever it is. What really matters to me is the concepts and the learning. Okay? I wish I could just take grades away and just be gone with them, right? Or I could just give you all A's, as they say, right? And plenty of people have asked for this, right? Now, I see both of those things as fundamentally unfair, right? I can't just abolish grades because half of you aren't going to show up, right? Unfortunately, grades are some sort of incentive for you to do number one, which is a 10. Okay, and that's really unfortunate. And I take that personally, right? If I say you're going to pass the class and then you start not showing up, I start feeling like you don't like my stories, right? Again, they're not my stories. This is scientific knowledge we're talking about, but I'm trying to make it palatable for you, to give you this knowledge, and then to also lace that with something you care about. Okay, so I take that very, very personally, right? I do this out of a love for this stuff. I do this because I think this is the most important thing in the world that I could do with my life, is to teach you about rocks. Well, not rocks, right? About the earth system sciences. So I can't just abolish the grades. People won't show up, and that's not how we do college. The administrators will be like, dude, you got to assign them something. And so the default then by you is say, well, give us all A's. Well, that's not really fair, right? Because some of you are inevitably not going to work as hard as some of the others. Some of the others that are driven to learn, they want to learn this information, and though it may be hard for them, they stay with it and they do a good job on assignments. They ask questions, they fulfill the requirements, they are earning an A. Does that make sense? Okay? An A is reserved for excellence. And I still uphold that. I might hate grades, but I reward excellence. Everybody else gets a B, right? You show up, you stay engaged, you stay up with the work, you're getting a B, okay? Rarely do I give out a C grade, and that's if the person has done exceptionally poor, okay? And by exceptionally poor is that despite all of my best attempts, you know, it's not just the facts aren't sticking with you, but that there's nothing. There's just very little that's there. There's something. You can recall some stuff, but it's very little. It's very few times that I'll give out a C, and I don't really want that to be an option, clearly. All right, so the weekly layout for the whole class, we have introduction to the new topic during day 1. Then day 2 will be more details or more depth about that, or sometimes we'll just have a new event, a related event. And then the third lecture, the third day that we would meet normally in a classroom setting, is to do a review, to work on a little bit of the homework questions together, to do some of the reading together, and then that's a quiz day. So a big chunk of the class is spent for some sort of quiz. Okay, so that's our basic layout. The heavy lifting is occurring on day 1 and day 2. Day 3 is for all of our benefits, and then of course a quiz. Okay, we're a little bit past the second hour of class, but I'm just going to steamroll through the rest of this now that we have all the other stuff out of the way, and we'll focus on geologic time, and that'll be the last concept for today with a short assignment. Okay, I say steamroll as if I'm going to like go faster, but how can I go faster? I'm going really fast. But I just have a lot of words to say. So I'm going to try to cut the words down a little bit because we will have more time to address this later. Most of the stuff that I've said today, I'm not going to dwell on again, right? I've dropped all the hints. We'll recall, we'll come back to that stuff. But today was a little bit wordy and exaggerated and all this stuff because it's the first day, right? I'm always tempted to just start off the first day with a whole heavy load of the same stuff you're going to get day after day after day after day. But there does need to be an element of keeping it light today. All right, so geologic time. This is a pretty good representation of geologic time where you had the geologic time scale, 4.5 billion years here. This is just the geologic, the Earth time scale. So the universe, the other 13.5 billion years or 11.5 billion years, well, 13.5 billion years of the universe, of which the Earth only occupies 4.5 billion. So the rest is off here. We're not concerned about that because Earth hadn't formed. And then of that, the largest chunk of time is something we call the Precambrian. Okay, the Cambrian is because that's the first division of the next portion of geologic time. So we say, you know, before you're mature, you're premature, right? I guess in the case of poor premature infants. But I hope that makes sense. That's where the wording comes from. Cambrian is a recollection from a place. That's how these conventions are named. So Cambrian doesn't really mean anything, but Precambrian just means before the Cambrian. Okay, the largest chunk of geologic time is the Precambrian, followed by these 3 other major divisions that we're going to use in this class. Those are going to be the focus of the divisions of geologic time. Okay, now it's important to recognize that each of those divisions can also be divided into smaller segments. This is just like a year, right? You can measure a year in hours, right? But that's insane, right? It's a lot of hours, and we don't have the time for that. So we chunk it up and we divide it up into different palatable chunks, and then we use those chunks depending on the context that we want to relay time, right? So if I'm talking about running a 200-meter dash, I'm not going to talk about it in months, right? We'll refer to it in seconds, right? Like 24. But if we are, we're talking about the length of my life, I'm not going to talk about that in seconds, right? That would be way too many seconds, and it would be a big number. So it's meaningless. So we divide things up, again, for our brain. So this goes back to that fifth principle, really, is that this is a scale model of time. So our brain, our mind can understand it and compartmentalize these things, right? So yeah, I want to say something about seconds and time. So I just mentioned my age in seconds, right? And how many seconds would that be, right? I mean, we could do this calculation, but I just want to think about this for a second. If you were to count, like by seconds, 1, 1,000, 2, 1,000, 3, 1,000, 4, 1,000, to do that and to try to count to 1,000,000, okay? A million. A million's it's a number you're used to, right? We always talk about millionaires or millions of stuff, millions of dollars, right? I guess that's the only context I have is money. Millions, right? We oftentimes talk about millions. It just rolls off the tongue. But do we really fathom what that word means? And I would argue, no, it doesn't really fit into our brain. That's why we call it million. 1 million, 10 million, 50 million. The million doesn't matter. What matters is the digit in front of it. So million then. If you were to count to 1,000,000 by 1 second at a time, that would take you about 11 and a half days. 11 and a half days to count to 1,000,000, right? Isn't that ridiculous? I mean, a few of you probably, while I was saying that, you're thinking like, yeah, I could probably count to 1,000,000, right? There are, and not, again, not singling you out or anything, but there are those gullible amongst us that would hear that and take that bet, right? You all know a gullible buddy, right? This is a great bar joke, right? Hey, I bet you all the money in my pocket, you can't count to 1,000,000, right? Then said person starts counting to 1,000,000, and then they've counted to like 500, maybe 1,000, and they still have a lot of numbers to go, and they realize that they're not going to make it to 1,000,000, right? At some point, that they might be bashing their head against the wall trying to make it for a while. But that is 24 hours a day. That is a ridiculous amount of time to spend counting, and nobody will win that bet. So if you get somebody to take that bet, you're the winner. Good luck with that. Okay. So let's talk about billions then, right? This is 1,000 millions, right? And if 1,000,000 takes you 11 and a half days, how about trying to count to 1,000,000,000? So again, if we count 1, 1,000, 2, 1,000, 3, 1,000. A billion would take you my lifetime, essentially, right? It's something like 32 years, 33 years. I'm 33 right now. To count 1 second at a time to 1,000,000,000, a number that we routinely throw around, talking about billionaires, right? $1 billion deficits, $1 trillion deficits, is a ridiculous sized number that we can't really understand. Okay, and if you want to learn more about that, on the next slide I have reference to this. But there's a lab, a scalar quantities lab that I'll post in on the supplementary folder for the class, And that scalar properties lab was actually taken from a colleague at University of Wisconsin-Eau Claire, Jeff Pinota. I think that he originally made that. If he didn't, then he should give reference to whoever did make it. But I got that from him, and then I've used that time after time again. It's a wonderful lab, scalar quantities. It's all about that fifth bigger idea about taking big things that we can't understand, like billions, and to reduce them down to things that we can understand. Okay, I'll come back to that in just a second. Now, I want to point out here, I have an asterisk for the next slide. When I'm talking about billions of years, okay, millions of years, previously, when we were talking about the biosphere or something, I said a few things about evolution, talking about the fossil record. If these are things that bother you, right, because of a personal religious philosophy, you may want to find a different class. We're gonna talk about these things and say these things over and over and over and over and over again. Okay. Now I don't want to say that you should just, right? I don't want to hear that crap, so I'm gonna leave. Okay, that's not a solution either, because this is the truth. This is the reality. And if your personal religious philosophy stands in the way of you accepting reality, then that's a problem. I encourage you to stay in the class and to continue to think about this so you can help your mind move beyond that. Now, I'm not saying to give up your faith or anything like this. Okay, that's fundamentally different. Right? And here's why. I want to spend just a second talking about this before we come back to geologic time, is that deep time and that concept is not a fundamental brutality on your faith and your religion. Okay? In fact, those ideas, those truths of the world around us, they are just that, they're truths, but they are not contrary to any religious beliefs. Okay? They instead are contrary to those that are arrogant in the religious beliefs. Okay? Excuse me. But it comes from the other side as well. Okay? So let's dwell on this for a second. So this is a note on young earth creationist religious philosophy. Okay? And you might be like, oh my gosh, where is he going with all this? Where is he going? Where's he going? Why is he talking about religion? This is a science class. Okay? And that's fine. This is the only time that we're going to focus on this. And that is solely because I don't want this to come into class later. I don't want you to continue to feel uncomfortable. I don't want hands flying up that are continually going to talk about young earth, stuff like this. So let's take care of that kind of right now. While religious philosophy is not within the scope of this class, it's imperative that we address this imaginary battle between science and religion. In fact, there is no such battle. Okay? No battle between science and religion. They're two different things that are asking different questions. Okay? How does the world work? That's science. Why are we here and what is my place? That's religion. Okay? Religion has no place in answering the hows of the world. Okay? In the book Genesis, the creation myth that is written there about God forming the world, or Yahweh, or Allah, depending on which of the monotheistic faiths that you follow, it is just that. It is a mythology, just like the Greek mythology, just like the Aboriginal Dreamtime mythology. These are ways that ancient people, 2,000, 7,000 years ago, were looking at the world around them and trying to understand how the world worked. Okay? But what they didn't have was a whole lot of knowledge that we've gained over the last 7,000, 10,000, or 2,000 years. Okay? Science is scientific inquiry, the scientific process exists for the how question, not the why question. Why did this happen? I don't know. How did it happen? That's a lot easier to answer. Okay, because how, you can pick up the pieces, you can see how they fit together. Why is fundamentally different. Okay, why is a consciousness problem? Scientists aren't trying to ask why. Okay, scientists are usually trying to ask how. And any kind of thing contrary to that, if you're trying to use science to support your claims of theology, right, or of there being a God, then you're not doing science correctly. You're putting the cart before the horse and you're saying, I have my answer, I want to use this tool to get to my answer. That's not how we do science. Also, it happens the other way, arrogance. If you are using science to prove, there's no proof in science, if you are using science as a tool to get to your conclusion that there is no deity, that there is nothing out there, that is again wrong. Because that is not the question of science. There is no scientific proof. Science doesn't have any sort of proof for anything. Science has evidence. And then scientists make probable conclusions from that evidence. Okay? We are in the business of observing and collecting data. And then when the overwhelming amount of those data show us something, we go with that. Okay? So this whole religion and science thing is garbage. Don't buy into it. It's a fight between arrogant people, and you and I are caught in the middle of it. Okay? In fact, some great religious leaders, like the Pope, right? Our current day Pope is also, he's a social leader, he's a religious leader, and he's a scientist. I mean, he's not himself a scientist, but he is very supportive of the sciences. And he is very outspoken about the need for humans to reduce our impact on the environment and to impact or to lower our impact for future climate changes. Okay, I find it very interesting that a modern religious leader is more well-versed in science than a fair number of our political leaders in this nation. Okay? Those people tend to put, again, the cart before the horse. And they're putting their personal philosophies and theology ahead of things that have no business in politics. Okay? So that's a little bit of my, my stuff here to kind of like lay it out there, that I'm not here to step on your personal philosophies about this stuff. You can have your faith. I have my faith. Okay? I'm also dedicated to a faith, and you can have yours. But my faith doesn't inform my scientific process, and my scientific process doesn't inform my faith. However, the conclusions that I draw from scientific processes and the conclusions that I draw from my spiritual feelings, they do combine within me, right? I can't help that. I am human. I am a subject, and I cannot separate those things. But I do not and should not and will not go out there and impose arrogance onto somebody else to say that I have the way. I don't have the way. It's mysterious. Okay? What we do know are scientifically collected data, and that's what we have. Okay? All of the other things are unanswerable questions. All right. I wanted to address for a second young Earth creationism. That's what started this whole mess anyway. Young Earth creationism is relatively new. Started in about the 1920s, and it was a reinvigorated subject that was really the creation thing, the reading of the Bible as literal, that had gone to the wayside in the 1800s. There's an article, if you click on this link here, that goes to the article. There's a PDF form of this. It's a GSA Today article, Geological Society of America article, on the evolution of creationism. This was written by Montgomery out of University of Washington. And he did a really great job. He also has a book on this subject, The Rocks Don't Lie, where he looked at this idea of creationism, right? And he looked at flood stories, he looked at the evolution of geology, the geologic sciences, and how, Christian geologists had put the flood myth to bed long, long, long ago. We had gathered enough evidence to say that that's a myth. That's not literal truth. Okay? These things are mythology that inform us socially, not real things and events that happen. So I suggest you go look at that article if you are skeptical about any of this, or you want to learn more about this part of this. And then this is just kind of silly, but for reference, in there, the young Earth creation philosophy typically holds the Earth as relatively young, formed in 4004 BC. Okay, and that number, which is ridiculous, right? I mean, we have written documents, cuneiform from the Sumerians that are much older than that. I mean, they didn't use dates because they didn't have the same dating scheme that we did. They didn't really care about dates in the same way. But we know that civilizations were far advanced by 4000 BC, right? The Babylonians and whatnot. So the posit that the Earth formed in 4004 BC was quite ridiculous, but at this time, there wasn't that archaeological evidence. James Bishop Ussher didn't have all the access to those things that we have today, right? And because we have that access today, we shouldn't remain as ignorant as somebody in the 1600s. But where he got this calculation, and you can do this on your own, it's actually a pretty fun task. I remember doing this when I was 7th or 8th grade, a young child in Bible school. I was inquisitive, and I did this. I did this exercise out of the book of Genesis. If you add up all the ages that are in there, so-and-so lived to be 120, and then they had a son named so-and-so, right? If you add all that stuff up, you make some assumptions about at which age people were having their babies, right? Then you derive a number that's not all that far off from James Bishop Ussher's number, and or James Ussher, and that number that he came up with, interestingly, 4004 BC. He actually gave a day of creation as well. I think what he says is that was the earth formed after the sun set on the October the 22nd. Okay, so therefore, when the sun rose on the next day, October the 23rd, the earth had been formed. That's my birthday, October 23rd. I was born at 1 in the morning on October 23rd, so just a couple hours after the earth formed. And I think that's pretty cool. Even though this is like a mythology thing, I still think that my birthday is a pretty cool birthday because of that. Okay? All right, anyway, divisions of geologic time. Yeah, we're getting back to it. These are formally adopted by the International Commission on Stratigraphy. So these aren't written in the rocks, as in like, here's the red layer, here's the blue layer, we shall call this one, this, and this one this. No, it's not written like that. This is a naming scheme that's come up with by humans. That's important to understand. So therefore, the rocks are not color-coded, so you do need to put conscious thought into understanding this. Okay, then those are relative ages, and then with the advent of radiometric age dating, 1930s, thank you, Madame Curie, for laying the foundation of that, and then more used in the 1950s, and so on to now, where we use it very routinely. Those give us absolute ages, and then on that older reference frame of relative ages, we've hung on that scheme the radiometric absolute ages. Okay. I've also already kind of said this, that billions are big numbers. So when we say 1 billion, 2 billion, what really matters there is the 1 or the 2, not the billion. I mean, that does really matter, but our brain doesn't comprehend it very well. So again, we use scale to scale things down. In this class, to talk about billions, we'll use the metric nomenclature of giga, like a gigabyte on your computer, on your hard drive. A gigabyte is 1 billion bytes. right? A terabyte is a trillion bytes, and so on and so forth. So we're not going to mess with trillions in the class. Nothing is that old in the universe. But we will use gigabytes for billions, or sorry, giga-annum years for billions of years, mega-annum, MA, for millions of years, and kilo, or Ka, for thousands of years. And we'll just use that nomenclature to shorten things up a little bit and to talk about numbers that our brain understands. 1s, 2s, 5s, 10s, 30s. Right? Okay, then the major divisions of geologic time, as we already stated, we'll focus on those major divisions. Here's that written out in the billions, but if we synthesize, or if we reduce that down into a simple number, it's a lot easier to understand. Okay, the 4 major divisions of geologic time that I want you to know, the Precambrian, that goes from the origins of Earth 4.5 billion years ago to a mere 542 million. That's a lot of time, right? That's the Precambrian. Then the next divisions, the Paleozoic, paleo standing for ancient, zoic, like zoology, or a zoo, that's life, or creatures. So paleo creatures, or things that look way different than things look today in the fossil record, basically is what they're saying. Paleozoic, ancient life. Then Paleozoic is from 542 million years ago, the beginning, to 250 million years ago, at which time there was a great mass extinction we'll talk about later in the course. And then we pick up on the Mesozoic, which is the time of the dinosaurs, the reign of the dinosaurs, later in the Mesozoic. That is from 250 million years ago to 65 million years ago. And then we have the recent time period, the Ceno, recent Zoic life. So in the last 65 million years, the evolution that's taken place, really the creatures look a lot like creatures that exist on Earth today. Not a lot, or well, there's a lot that's changed, but not as different as, say, the dinosaurs or the trilobites. Okay, then a lot of the events that we're going to focus on do happen in the Precambrian, but it's not because the Precambrian was unusually violent. Well, maybe during the Hadean, the origins of Earth was a little bit uncharacteristically violent during the early bombardment phase, but the Precambrian really wasn't inherently violent. It's just that it's so much time that all the really cool things that we're going to talk about, a lot of them happened during the Precambrian. Okay? All right. Here's a really good analogy of geologic time. So again, maps, models that scale to our human brain helps us make sense of all that stuff. I showed you one image of geologic time, but you'll find many people make comparisons to everyday items like a clock, a 24-hour clock. If we were to hang geologic time on a 24-hour clock, then things like organisms, first plant life appears in the form of green algae 3.5 billion years later. Okay, so most of the clock is relatively empty as far as in context of life, but mind you, there's a whole lot of geologic things going on in this time. All right, so we're not necessarily going to use the clock for our class. It is a good model. I should point out that humans show up at the basically the last second here before the 24th hour. That's how young our species is. But the clock, this is a good one. Go visit this site. This is called This Is Today, and they lead you from a box that looks like today, and then they show you what that box looks like in context of geologic time. It's pretty good. And then I commonly, because it's really handy, I commonly use the analogy of my arm to describe geologic time. And the Precambrian goes pretty deep into my arm, and then you have the Paleozoic and the Mesozoic and the Cenozoic taking up a relatively small portion of that. So the human arm is a good thing to use as an analogy. Well, in this class, because this is 10 weeks long, we're going to use this calendar, a 10-week calendar, to hang our events on, okay? So we're going to take each event that we study and say that it happened 4.5 billion years ago, we're going to place that properly on the calendar when that happened. So if it happened, this is today, 4.5 billion years ago, that would be over here on day 1. Right? Hopefully this makes sense. This has led to some confusion in the past. This is not a schedule. So when we talk about, say, Pleistocene glaciation in week 3, that didn't happen billions of years ago. The Pleistocene glaciation happened relatively recently. So you would place that event here, even though in class we talked about it during week 3. I hope this makes sense. We'll work with this a little bit more, and the first exam will show us whether this makes sense or not. So each day is worth a certain amount of time. And that brings us to your first assignment. Okay, so your first assignment then is to calculate the length of time for each day. Okay, should be pretty easy. You can email me questions, things like that. Catch me before class. I want you to work through this a little bit, but it's the same calculation if you're calculating, say, miles per hour. Right? They're really, instead of traveling a distance over a time, you're doing something a little bit different, but it's really the same, no, it's not a conversion factor, but it's similar math. Okay? Then the second the second part of this assignment is that I want you, using the first one of these principles, that the Earth is a system of systems, I want you to write me a narrative about how each of those systems are connected to the others by the second principle, by the flow of energy that drives matter. I gave you at least one example for this. Actually, I think I gave 2 examples, one about meteorology and one regarding the sun. But there are plenty of examples that are out there, and I want you to start thinking in this systems process. This doesn't mean to be perfect. This doesn't mean need to be impeccable now. What I want you to strive to do is to talk, to hit each of the 5 spheres, right? The heliosphere, the atmosphere, the hydrosphere, the geosphere, and the biosphere, all of those at least once, and then to attempt to talk about their matter and how energy, the flow of energy drives the cycling of the matter. Okay, I realize you don't have a huge background in any of these sciences thus far. Just use what you have. This is going to be a building assignment, so this will serve as your first, and it is the first of the assignments that you'll get credit for, but we're going to keep building this narrative. In fact, this is the biggest question, the largest, and worth the most points on the final exam. Is this exact same question, but by that time, 10 weeks after today, you will have done this over and over and over, not the same thing, but added to this given your understanding in the class. So attempt this now. At the beginning of next class, we will do both of these pieces of work, and we'll move on with the very first the very first subject of this class, like real subject this time, which is kind of the basic chemistry of the Earth. Okay, remember I said in my geology classes, I want you to treat the Earth like a friend, like you're getting to know the Earth. Well, in this class, we're just like going past the getting to know you thing and going right to bed with the Earth for the good stuff, right? Excuse me for like the one night stand reference there. What I mean is that we're getting to the juicy details of the Earth without really getting to learn about the Earth, okay? So it's all that I can do in the geologist in me to not, spend a whole lab period or a whole time focusing on each of the types of rocks and things like that. It's hard to not do that when I'm asking you to evaluate the Earth in these other ways. So we're going to spend one full day, lecture day, focusing on the Earth's materials and just kind of catch you up on what you might see in another geology class. And that will serve as enough of a survey of geology for all the big bad subjects we're going to talk about later. Okay? All right. And with that, we're finished up for today, and I hope you have a great rest of your evening, and we'll see you next time.